Hey, Nihar, are we ready?
Yes, let's get started.
Okay, cool. All right. Hello, everyone. Welcome to our workshop. There is the fourth workshop of open world, namely visual perception and learning the open world. My name is Shu. I'm one of the organizer in this workshop. So first, I want to welcome you to this workshop. I hope everyone is safe and healthy. The goals of the workshop is to connect people and exchange ideas about the open world vision, and we should discuss new opportunities and challenges about the open world. This is a hybrid workshop. We have on-site participants, so please enjoy and involve by asking questions. And we also have an online Zoom link provided by CVPR conference. The schedule is like this. You can search open world learning on the website to find the link to the workshop website. We have 4 challenges listed below. You can refer to the agenda and come over whenever you like. I want to thank all the speakers, organizers, advisors, coordinators. We have smiling faces of them, so you can say hello to them and they will greet you as well. First, I want to introduce the open world a little bit. Firstly, we emphasize testing in the open world, but we still train models in a closed world. For example, we have an open set recognition, which means that we train models on some closed set, and we emphasize that we have a never before seen novel examples in the testing scenario. That's why we have to detect the novel stuff. And later we have an open world recognition, which emphasize, we should not only detect the novel species, but also do some continual learning for the novel species with human annotation in the loop. These are the old days, but now I want to make an argument that we nowadays train that open world. For example, we sample data from the open world for better open set recognition, where we sample outlier data or outlier exposure to train better models to detect a never before seen novel species. And I want to claim that foundation models are actually pre-trained in the open world. For example, CLIP. With the open world models or foundation models, we can do open vocabulary recognition. We can do zero-shot recognition, so on and so forth. But here we want to think, okay, we train foundation models in the open world. Can we predict testing performance with the distribution shift? Given that we train in the open world represents some data distribution, but in a downstream task, we have some distribution shift. Can we predict the performance? I want to remind people that this is actually an established problem, which we call, we train in some in-distribution data, for example, ImageNet, but we test on some domain shift data or out of distribution data, ImageNet V2. So can we do this? Can we predict the performance? Actually, people report that we can. We report accuracy on the line observation, meaning that empirically we see OOD performance is strongly correlated with the in-distribution performance for a wide range of models and distribution shift. But here I want to remind people that the models tested in this scenario are trained in a closed world, and we wonder, does this conclusion still hold if we test the open world data, open world models? And here we tested 75 models, including vision models, vision language models, trained in neither the closed world, i.e. ImageNet, or the open world, which represent the data from the internet. And if we draw this line again, and we do the scatter plot, we see that accuracy on the line does not hold anymore. But we see another interesting metric, LCE, or least common ancestor. If we use that metric to draw the scatter plot, we see LCE is on the line, no matter what models we train or in what scenario, open world or closed world. But here, I want to quickly explain why. The intuition is that if a model can make better mistakes measured by LCA, it can mitigate a spurious correlation leading to better generalization. This is a work published by our group at the ICML. Okay, and here we see that, this is a very exciting scenario, a very exciting conclusion that we can predict open world models on any downstream task. But if we dive into some failure cases, we see some interesting examples. For example, I work on species recognition. I threw in some species names like this one, Panana citrina, and I asked the GPT-4 to describe the visual features of this species, but GPT-4 fails. This is surprising because we can sort of believe that GPT-4 is already trained in the open world using all the internet data, which OpenAI can obtain, right? But why it fails? If you search Google, you actually can see some examples and some descriptions in this website. Why it still fails? My hypothesis is that some concepts, especially scientific names written in Latin, are too few in the open world to train models. But how to justify this? We count. How we count? We use some open source pre-training data set like line 2 billion, line 400 million. If we count, we see that, okay, the Latin scientific names are actually very few sampled in the open world. This is not the end of the world. This is not we have some tricky remedy like this. Given a scientific name for zero-shot recognition, we translate the scientific Latin name to English common name, and we use the English common name in the prompts to prompt the pre-trained foundation model or vision language model to do zero-shot recognition. If we do so, we can significantly boost the zero-shot recognition performance, that is zero-shot accuracy on 2 data sets. As name is the scientific name prompt, common name, this is the same name, right? This is interesting. And we want to test more data with diverse foundation models. For example, I threw in this image, which is a night snake. Night snake is a category listed in ImageNet, and we ask the question, ask GPT-4 and some other foundation models, what is the species name of this animal in the photo? And none of the foundation models can answer this question correctly. And we also ask DALL-E 3 to generate a photo for a night snake, and they fail. This is, again, very, very surprising. My hypothesis is that certain concepts are insufficiently presented in the open world. Examples related to these kind of concepts are very few to train a good foundation model. So we have some evidence to show this. We have a way to measure the concept of frequency in the open world. And here we use the measure. I will describe how to measure the concept of frequency. Just imagine that we have the measure, and we can draw this curve, which is a concept of frequency in the ImageNet. We sort them from low to high. This is the imbalanced distribution of very obviously. And we also draw this kind of a curve, which is a zero-shot accuracy for the ranked class names. And we see a strong correlation between the concept of frequency and the per concept accuracy. This is a kind of evidence showing that certain concepts are just a few in the open world to train reliable foundation models. Okay. Now I want to show you how to measure concept of frequency. Of course, we still count. intuitively, we can count the occurrence of pre-training tests related to the concept of interest. But here we have a challenge. Pre-training data is a large scale. We have billions of training examples. So how to do a reasonable measure? Here we use string matching. String matching is quick, is efficient, but we have two more limited hurdles. The first one is the lexical variation, i.e., there are some synonyms. For example, for the running shoes, we have other names like sneakers, trainer shoes, so on and so forth. A second hurdle is that the linguistic ambiguity. Just remember that we use string matching. We want to find tiger, but we still have other sort of non-tiger examples like tiger shark, tiger woods. Obviously, the latter two are not a tiger animal. So how to address this issue? We come up with this flow chart, this pipeline. To deal with the lexical variation, we ask a large language model to list the synonyms for concept of interest. This one is the tiger. We ask the question, what are the homonyms or synonyms referring to tiger? And the large language model can give us some candidates, and we use all the candidates to search the relevant pre-training text using string matching is here. And later on, we use another the same language model to filter out irrelevant captions. For example, we ask this question: does this concept in the caption referring to tiger? And we can filter out some ambiguous, irrelevant captions. This enables us to reliably measure the concept of frequency. By doing so, we can draw the curves and show the strong correlation between the concept of frequency and per concept zero-shot accuracy, justifying that some certain concepts are just a few in the open world to train foundation models. There are some interesting insights. For example, if we do zero-shot recognition, we can translate the given concept name to its most frequent synonym in the prompt. If we do so, we can significantly boost the zero-shot accuracy. Another insight is that we can do retrieval augmented learning. I just want to give people a little background. There's another paper published last year called REACT, which is the state-of-the-art retrieval augmented learning method for zero-shot recognition. Basically, if we care about one concept, we can search relevant examples on the internet or in the pre-training data set of a vision language model. And after we retrieve a bunch of examples, we can train a new model for recognition. Here, people just use the original concept name. But now we know there are some synonyms or other common names. If we use all the common names or synonyms to do the retrieval, we can retrieve more relevant data and train better models. That is our method. Now we use all the synonyms for retrieval augmented learning. We can outperform the state-of-the-art REACT by a large margin. And I want to remind people that when they do retrieval, they compute the image features or text features, but we now use string matching, which is pretty fast. By doing so, we can reduce the computation cost significantly by orders, right? Another insight is that we can use the most frequent synonym in image generation. For example, here, if we want to generate an image for bank swallow, we can, of course, ask DALL-E 3 to generate a photo of a bank swallow, but DALL-E 3 can fail because we know the reason. Bank swallow is not commonly represented or presented in the open world. That's why DALL-E 3 fails. But now we can find its most frequent synonym which is the Saint Martin. If we replace bank swallow with the Saint Martin in the prompt, we can let data 3 generate the correct image. This is our paper. We will present the paper later in the conference, so please come over and discuss with us. All right. I want to conclude my very short talk with 3 remarks. The first one is that foundation models are open world models. We train models in the open world, and yeah, that's pretty cool. And the second remark is that open world models have open issues. The open issues are mostly related to open world data. For example, the data is long-tailed distributed. It has some domain shift, so on and so forth. All right. That's all about my introduction. So I hope everyone enjoyed the conference, enjoyed the workshop. So Nihar, please take over.
Great. Thanks so much, Hugh. All right. Walter, why don't you come up? Our first talk today will be from Professor Walter Scheer, who is a professor at Notre Dame. He's been doing many pioneering works in open set recognition, and he's been leading the field for more than a decade. So today he'll be presenting his talk, Open Issues in Open World Learning. And I think this will be a very exciting talk. So please, Walter, take it away.
Learning. And so I want to talk about to continue working on. So I'm going to talk about some of these that are sort of the most salient things I think we should all be thinking about. But to begin, let me talk about why this is such an important problem, and a little bit of how the computer vision community has underrated this problem historically. Asking a question here, why don't we have self-safe driving cars in 2024? Those of you who have been attending CVPR for the past several years know this was a pretty hyped up area, right? A hyped up application area. Elon Musk, even before this was like reaching its apex in like 2019 in our community, was saying, Teslas are going to be like level 5 autonomy, next year. And he said this over a series of years. And we never quite got there. Now, of course, again, if you look at our expo, which is opening up tomorrow, almost all of those self-driving car companies have disappeared. They've gone out of business. They're being wound down. What happened, right? I think a big piece of the puzzle when it comes to autonomous vehicles in general is, in fact, the novelty problem. Driving is really tough. There's lots of stuff that can appear on the roads. For instance, think about new objects. In much of the history of the automobile, the smartphone did not exist, right? Not only is this a new visual object, right, that could be recognized in a scene, it also changed user behavior, right? Interactions between users changed, interactions between users and the road environment changed, right? All these things were new, right? Things in terms of the behavior of pedestrians that were simply not observed, right? And things like this, of course, will happen time and time again. Another interesting thing, which is also terrible, if you dig into recent accident reports for Tesla's autopilot system, some strange things have been happening. For instance, the car with autopilot engaged will approach the scene of an existing accident and drive into it. Why is that happening? Well, these are rare instances that aren't reflected well in the training data. And also, I'd point out, accidents aren't well characterized, right? There isn't like a stereotypical accident scene, right? The configurations of the objects are going to be different. There's going to be, right, different numbers of emergency responders and emergency vehicles, all these different things. So that's something that's really hard to learn. And right, it's a novelty that the car is simply not managing well, right? You get a secondary crash, which in some cases, right, has been catastrophic. So like all of that's pretty bad. And I want to point out the fundamental shortcoming here is one that's related to this big data strategy we've been pursuing in machine learning for a number of years. Right? It's always going to necessarily undersample the physical world, and often drastically. I think that's surprising to a lot of computer vision researchers because we've been brute forcing a lot of other problems with web scale data for a long time. But again, the physical world, there's just so much that can happen. Neil Lawrence actually pointed this out a number of years ago, just as, again, like the self-driving hype was reaching its apex on X. He noted that there are countably infinite things that can possibly happen on the road. So if you acknowledge this, you know then that you're going to have to do something else when it comes to novelty, right? There's no way to brute force this. You're going to have to come up with a scheme to basically identify it, to characterize it, and then to manage it in some way. And so all of those were objectives of the DARPA Salon program, right? Is the sort of like government folks had known this for a number of years, right? That this was, you know, something that was inhibiting like really good mobile robotics, right? Autonomous agents and other settings. Another thing, again, perhaps again, people working on this problem, this isn't surprising, but researchers have been looking at really simple environments and adding novelties to them and noticing, again, a drastic impact on the performance of agents and recognition algorithms in these environments. Environments as simple as cart pull, right? It's like one of the simplest AI tasks, right? Like balance the beam, right, on the cart. There are fun ways to sort of add novelties to even these very simple environments like cart pull. For instance, changing the physics of the environment, perhaps varying the force, right? The complexity of the task then goes up by quite a bit. This was actually one of the environments that was being studied in the Salon program. Really simple data sets in computer vision, like CFAR10, hold out some of those classes, right? They become novelties, and the task becomes more difficult, right? And folks have done this, right, with all sorts of different simple data sets, MNIST, letter, right? All these really basic things we've assumed to be solved, right? You add the novelty, and all of a sudden, right, a lot of our best approaches are starting to struggle. Like, why does that happen? As was noted in the introduction, right, for many years I've been studying this problem, and a long time ago now, we sort of came up with some reasons for why this is occurring in a machine learning setting. For instance, right, if we look at the training data, we're always going to have incomplete knowledge of the world at training time for these open world domains. Because again, we simply can't brute force this at training time. There's always going to be new things. But why does it fall flat, right, in a classification sense? It comes down to the basis for making a decision. There's no basis from which to generalize to novel data from known data, both of which are typically far away from each other in some feature space. And if you're dealing with things like linear classifiers, this is really dangerous because you get these infinite half space effects. Where again, you have a nice clear decision boundary, but this novel thing is appearing way out there in the feature space, far from the support of the known training data. And of course, right, you get misclassifications. The same thing happens too in a slightly different way in a nonlinear context, right? So if I have a really tight boundary around my known features, I still, right, then have problems generalizing to new samples of the known data because I don't get good generalization. And in some cases, again, the feature space has a lot of aliasing, and it's hard to make those distinctions. With respect to the novelties themselves, new things, as I pointed out, are always going to appear in an open environment, right? This is a fundamental aspect of the environment. And it's not restricted to object classes, right? This is something I think that's also underappreciated by a lot of folks working on these problems. Mainly because the literature has been focused on, right, object classes thus far. And again, that's part of the puzzle, but it's not the only thing. I want to point out that novel activities and interactions are also really significant confounds that you're going to have to think about. All right, so again, if you're in machine learning, you may be thinking, well, wait a minute, right? Like, we can probably manage novelty using reinforcement learning, right? Isn't that the point? We're going to go through some iterative process, right? We'll get some new information, right? We'll learn that information, incorporate it back into the model, perhaps with some human feedback, right? No problem. Well, think about this, right? Sort of in the limit, right? You can't, number one, have somebody in the loop doing this all of the time, saying this is a novelty, this is a novelty, this is a novelty. That means you need a really good automatic novelty detector, right? To automatically figure out that this is something that's new. Now, that's potentially dangerous if you just blindly learn it, because there are many novelties that we don't care about. In the Sail-On program, one thing we recognized quickly was the importance of making the distinction between novelties you care about and novelties that you don't. And we called those novelties that you don't really care about nuisance novelties. So we all know it, like the area of anomaly detection, right, has been pretty well developed over the years. There are lots of different anomaly detectors, but they're really not good at characterizing novelty. In fact, almost all of them don't do that. And so if you think about the world, there are plenty of things that change that we simply just don't worry about. For instance, right, this room, if I have an autonomous agent traversing it, it has a visual recognition system. If it turns out the color of this carpet is a novel shade of beige, one that has never been seen before by the system, that's a novelty. But does the agent care about it? No, right? It's totally irrelevant. But if that's being flagged by some anomaly detector as something to consider, right, and especially in a reinforcement learning regime, all of a sudden you're ballooning your model, right? Because you're ingesting all of this irrelevant information. So out of the box, reinforcement learning is not going to help you inherently. And again, this comes up quite a bit, which is surprising to me, right? It's like a lot of researchers just think, oh, this is it. You know, it works in so many other domains. Don't worry about it. That's not true. Okay, so if you're going to build a really good open world agent, what would it look like? Probably something like this, right? It's going to have these three pieces that I mentioned. Novelty detection, novelty characterization, and then some form of incremental learning to incorporate the non-nuisance novelties, the important novelties that impact agent performance back into the system, right? So the input is going to be some sort of image or video. Of course, you're going to extract features, right, or learn features from that data. You're still going to have a classification component to this, right, which will probably be task specific for whatever you're doing. And then you're going to move on to this novelty recognition process. You're going to detect novelty, characterize it, and then figure out, you know, is it important, is it not? You could have, right, external feedback. There could be a human in the loop. But again, that doesn't scale, as we all know. So that's going to be a factor. So a few notes to this basic template. Number one, novelty detection and characterization turn out to be really, really hard. And again, if you've been working on this problem, you know that. Number two, efficient incremental learning is necessary. There aren't that many really good incremental learning classifiers out there. A number of different groups are working on them. I've done this in the past, but there isn't something that I'd say is like off the shelf great at this point. And a related note to that one, classifier research is just not very popular right now. Right? You know, I think like part of that's just the trends of the field, right? It's like representation learning became hot, and then we heard, you know, if you have really good representations, you'll get great separation of the feature space. Use any classifier, any basic linear discriminant will work great. That turns out not to be true. And again, we've been thinking about more complex features to that, like adding incremental learning, that's an issue. Everybody's excited about generative models, generative AI, right? So I feel like more folks need to come back to this problem because there's some big open questions that we're left with, which are important. Okay, so let me talk more about DARPA Sail-On before we get into some of the big open issues that came out of the program. So DARPA Sail-On was really interesting because again, I think it tried in a rigorous sense to find a bunch of different domains that varied quite a bit in different modes, not just computer vision, but also thinking about interactive domains like games, thinking about vision in different instantiations, activity recognition, object recognition, handwriting recognition, right? Lots of different data domains. And again, pushing this point that we should have some kind of domain independence, right? If we're building these systems, right, the ideal would be the agent is moving seamlessly across the different domains. And that's something I think is kind of shocking to the computer vision community, because typically you're working in one domain, you have a very specialized approach specifically for that domain, and you don't think about, right, it generalizing to perhaps radically different domains with very different data, interactive in some cases, right, not just static images, but the program folded all of these things together. The program also had a very specific notion of novelty and how it's sort of introduced into an environment for evaluation purposes. This was called the big red button. So you imagine there's an agent, it's in some domain, right? It's operating, as it's been trained, right? Or as it's been programmed if it's procedural. A button is pushed somewhere in the universe and something fundamental changes in that domain. The agent doesn't know this has happened, but it's expected to detect that change and be able to manage whatever novelty has been injected, right, into the environment. So, right, something, if you think about this in like a distributional sense, right, like the distribution is now different in terms of the data that are being ingested by the agent. The agent's got to figure that out on its own and then adjust accordingly. And that's kind of how each evaluation proceeded throughout this program, regardless of the domain, right? The domains were quite different, right? So again, it was like everything from like carpool to like visual object recognition, VizDoom, Carla, like the autonomous vehicle simulator, like all these different environments, but they would all sort of be structured around the same idea. What was also interesting, again, moving beyond just this notion of object classes when it came to novelty. The Sail-On program organized things like most DARPA programs in different phases. They had 3 specific phases that they carved out where different aspects of novelty would be analyzed. So in phase 1, we indeed did start with just objects, right? So this is like new classes, attributes, and representations. But in phase 2, we were looking at novel agents, right? Novel things interacting with the agent that like we sort of designed, right, in the environment. Actions, right? Like how are these things behaving, right? If it's an interactive setting, or even in computer vision, right? Novel actions reflected in a recorded video sequence. Relations, right? If there are different objects in a scene, how are they related, right? Do those relationships change? Again, something that we typically don't think about in computer vision, but that's something that's quite consequential, even in still images. Interactions, again, there are different ways of objects or agents interacting in some environment, right? I already pointed that out as a confound for self-driving cars because like pedestrian interactions change as we introduced the smartphone. And then in phase 3, we looked at more complex phenomena. Rules, right? Especially for game playing, right? What happens if you change the rules of a game like Monopoly, which was another one of the domains that we considered in the program? Can an agent figure out that something has shifted because the points being assigned, right, are not the same in terms of the gameplay? Goals. Can you change, right, the goals of perhaps winning a game without telling the agent? Does the agent figure it out? And then events, right, like big things, right, that are sort of introduced into an environment that the agent will have to negotiate. Again, an event could be compositional, right? A lot of different things have changed that's all building up into one big event, right, that has to be negotiated. And so, again, I think this is interesting, but when we're thinking about open issues, right, this hierarchy is pretty arbitrary, right? It's just the organizers of this DARPA challenge came up with this, right? And so we could probably think of more things to add to this. We could probably fold some of these things together, right? This was sort of an initial cut at coming up with, right, some structured challenges for the program. Okay, another big thing, the metrics. How do we assess open world recognition? Again, I see a lot of heads nodding here. We know in the literature that many things have been tried, right? Everything from like very basic classification measures, right? Because ultimately, if you're thinking about a task like just open set recognition and object recognition, you're thinking about like the accuracy of the classifier in some sense, right? And of course, right, accuracy is not a great metric if the distribution is not balanced in terms of like novel things versus known things, right? So we sort of know that, and, things can get buried. If it's like some sort of classifier, right, that always says everything is novel, and you've shown it mostly novel things, right, the accuracy is going to be high, right? So there's some ways to game the metrics there, which isn't great. So in literature, including my own papers, we looked at other measures like an F1 score, precision recall, right, things from information retrieval, but all of those, again, sort of have different pitfalls. That said, you need some metrics, right, to figure out, is the detection part of this working? And so the Sail-On program looked at different specific measures for detection, right, coming, down to basically this measure of like correct detections and also false positives. Is the detector working in some rigorous sense? But that's only one piece of the puzzle. As I pointed out, right, the program, and I think researchers overall are really interested in these three things, right? Detection, characterization, accommodation, right? Or, that's the incremental learning piece. Weirdly, characterization, nobody could come up with any good formal metrics. That remains an open issue. So the program skipped ahead to accommodation, right? How well is the agent responding to changes in the environment? So there were metrics that were formulated sort of like pre and post red button push, pre and post introduction of novelty. What happens to the agent's performance? And so these various metrics were sort of proposed, looking at like different ways of assessing the ability of the agent to sort of like perform in the environment, to learn these new things, right, and perform different temporal sort of aspects of that as well. This was sort of a good first cut, but again, we need more work there. So what did we learn out of all of this? As I mentioned, right, this talk is really about the open issues, and I want to like spend the rest of the time talking about the 8 big ones, which cover these aspects and some other ones which I think are really interesting. We organized these in terms of 3 different categories related to novelty. Number 1, theory of novelty. As it turns out, there's a lot of good theoretical work out there in the computer vision community, especially on like what is novelty, right? Are there other communities thinking about this? Yes. Stand by, we'll talk about that. Design of agents. That's mostly what we spend our time doing, right? Building algorithms, right, to tackle this problem. But as I mentioned, right, there's some really interesting big open issues there. And then finally, what I was just mentioning, just introducing evaluations. Are we there yet when it comes to the metrics? Are we there yet when it comes to actually organizing benchmarks, right, for us to assess whether or not this is actually working? And it's tricky, especially, right, this is open world learning, information leakage, right? That's really dangerous, right? So trying to mitigate that is going to be a big thing. So as mentioned, yeah, let's talk about these 8, right? The need for better developed theories of novelty, differences between activity and perceptual domains, domain independence, better representation for novelty learning, robustness to novelty versus novelty detection and characterization, risk-based reasoning, spectrum of partial knowledge the system designer has about novelties, and the lack of measures that are really specific to open world learning. Yeah, plenty of time here to wrap this up. Okay, so number 1, the need for better developed theories of novelty. As we embarked on the Salon program, it became apparent, what were we working from? Like, what are the assumptions? Like, what are the first principles? Turning to the literature in pattern recognition and artificial intelligence and computer vision and natural language processing, there wasn't a heck of a lot, right? And so that meant we had to go back in time, all the way to Plato, right? You don't typically get a talk on Greek philosophy here at CVPR. But it turns out Plato, in one of his Socratic dialogues, actually considered this question of what does it mean for something to be novel? And it actually has some interesting advice for us today for artificial intelligence. Plato claims that new things are generated by reconfiguring existing material into a new form through the guidance of set patterns. Interesting. So you could think again about some kind of generative universe, right, where some things are kind of fixed, like say the particles in the universe, the forms of matter, etc. There are great rules of physics that the universe needs to conform to create things that we assume to be new. That's kind of interesting, but perhaps not entirely practical for our purposes, right? Because we want to figure out, is there an algorithmic way we can sort of, reason about all this? So flashing forward to another philosopher writing in the 20th century, Thomas Kuhn, who was also thinking about this. Kuhn argued that novelty reduces to the perception of things in an environment that are new to the observer. This one is very interesting because as we know, we won't have comprehensive knowledge built into any agent that we program, that we train, etc. And some things that are perhaps known to us humans may not be known to the agent, but the agent is going to have to figure them out eventually, right? Especially if they impact some task performance. So this really becomes a matter of, is it new to me versus is it new to the universe itself? That said, folks within the DARPA Sail-On program were really interested in the environment, not necessarily just this agent-forward perspective. For instance, Pat Langley, who some of us probably know is a really sort of old school AI researcher, who knows a heck of a lot about machine learning too. He was really interested again in this sort of generative mode that the environment operates in, and argued that environmental change in a strictly generative mode is the basis of novelty, right? You have to sort of reason about novelty from this environment first perspective, right? And so there was a lot of debate within the DARPA Sail-On program about these two perspectives, right? Is it the agent's observations, or is it really something fundamental in the environment? And there's arguments, for and against all of these things. I landed, I and some of my colleagues landed on Kuhn's sort of, perspective here, just because it's more practical when you're sort of building these agents, right? I can't comprehensively account for everything in an environment, right? That's really, really difficult. But I can, in an easier sense, figure out this is new to me, right? I can formulate an observation sort of way to reason about these environments. That said, so in a paper we had at AAAI in 21, we did sort of break this out into things that do change in the world, but again, in a dissimilarity measurement sense, so that still conforms to what Kuhn is saying. From the agent's perspective, in an observation sense, so I'm sensing information from that environment where something may have changed, or maybe nothing has changed, I've just encountered something new. And I'm, again, performing a dissimilarity assessment. And I'm also factoring in my regret, right, is I have to solve some tasks, will this actually impact me or not? And that's really consequential, as I pointed out, for managing nuisance novelty. And that I think is probably the more tractable approach, right, instead of accounting for everything in the universe. But still, there are open questions when we think about these theories. Given the two overarching framings of environmental novelty and agent-centric novelty, is it possible to reconcile them into a single theory? Is there any theoretical basis for a novelty hierarchy? As I mentioned, DARPA kind of came up with that, right? The creators of the program came up with that. But we can probably think of more things to add to a hierarchy. We can probably think about rearranging that hierarchy in other ways, eliminating some things, adding some things, right? All these things are possibilities. I think, again, all of that's sort of built out of assumptions we make about our tasks, right? And that ties it then to some domain, which could be dangerous or maybe not. And does any extant theory help make predictions about agents and their interactions with the environment that can help guide agent design? Because what we want are better autonomous agents, right, that handle all these things. Okay, a second theoretical concern that came up, differences between activity and perceptual domains. As I mentioned, the DARPA Sail-On program had interactive game environments, in some cases that didn't have any vision component, and they also had just straight up computer vision data sets, right? All of these things were seen as being places where novelties could occur, but what the real goal was to have some sort of, agent that could cross them seamlessly. That's really, really tough. Right? Because again, if we look at activity domains, right, the artificial intelligence community has a totally different set of planning-based techniques. Right? In some cases, there may be a vision component, usually not. On the flip side, right, we typically don't do planning for static image sets, right, for object recognition because there's no temporal dimension, right? There's nothing to plan. This makes this really, really hard to sort of, unpack. But again, if people can seamlessly cross these domains, why don't we have agents that can do it, right? That's a big question. Can the two be reconciled? I mean, there are some hints that this is possible. Mobile robotics, right? This happens all the time, right? It's I need a vision system in many cases, right? Some piece of it is trained on static images, but it's on an agent that is operating in the environment. Now, of course, I hear complaints from my roboticist colleagues all the time. Computer vision, you folks created these highly accurate object recognition systems, right? These great neural networks trained on these data sets from the web scale data, right? The papers look amazing. The benchmark numbers are so high. I put this on my mobile robot and it's just misidentifying everything. It's crashing, it's exploding, right? The magic smoke is pouring out of it. Why is that happening? Good question, right? Because it's a domain shift, right? There's a problem there. Something though I think perhaps is a little bit more useful for thinking about this. like remember like DeepMind style video game play, right? Remember like 10 years ago, it was like really like exciting to, and OpenAI was doing this too, right? It's like you have a vision system that is playing a video game like a person is playing it, right? So it's doing all of the visual recognition, and then it has like the planning pieces, right? And playing the game like a human player is playing it, you know, in the sort of back end as well. That's really, really interesting. Predictive coding is a classic idea in computer vision, which also has a temporal dimension, but it works for fixed images. I think that's another way to sort of bridge this gap. And then this notion of dissimilarity assessment through agent observation, right? That's another way you can sort of reason about this. So again, I think there's some clues, right, and some also prior work that fits this regime really well. Okay, the third thing, so going into the design of agents, domain independence. We've heard all of these bold claims about deep learning generalization, but they've really never been true, right? If you think about deep nets, they're basically limited to just a single domain, the one associated with the training data. You know, when we think about generalization, it's usually like generalizing to new instances, usually objects if it's object recognition, within that one data domain. But the Ceylon program had this much broader notion of domain dependence, right? Where it's like I should be able to move from object recognition to, say, an interactive car simulation environment or a video game environment or anything. Planning, of course, suffers from a similar problem. If an agent moves to a new environment, the old plan may provide it no useful information, right? Everything has been intentionally designed for that other domain, which is an issue. So the big challenge is crossing between activity and perceptual domains. Is it possible to have a feature representation that applies in a universal way? No such feature representation currently exists, right? So that's a big constraint. One possibility is, though, to pick a universal representation, perhaps something like a spectrogram, which has been suggested in the machine learning literature, and transform all of the data into it. So maybe that works. One then would be left minimizing domain dependence rather than achieving strict domain independence. Because ultimately, again, you're going to need some sort of domain dependent information. For instance, like the sensing, right? There's got to be some piece of this system that interfaces with the domain in an intentional way. All right, a related issue too, better representation for novelty learning, right? So a few more thoughts on this idea of representation. There is an intrinsic link between the goodness of a representation and the ability to detect novelty. If known information can be clearly represented, then what is different from it can be discerned without significant effort. But of course, as we know, again, a lot of us have been training systems to do this, right? There's too much aliasing between the known and unknown information. You're gonna get a lot of false positives and false negatives, right? That's bad. So like, what can we do? One thing that surfaced, which I think is kind of interesting, is the notion of a representation edit distance. This is suggested by Josh Allspector recently. It actually builds off of some earlier work suggested by Francois Cholet of Kira's fame, who's been out there more recently, like with these grand challenges on like human level, cognition, right? But he has some interesting things to say about representation too when it comes to these problems. Perhaps, right, we need a measure of novelty that can be used by agents to adapt to it. And a change in information content in bit strings, if you think about this in an information theoretical sense, could be measured by comparing pre and post novelty skill programs. What's nice about a bit string representation, again, I was just talking about, like, is there some common representation that's useful across radically different domains? This is one of them that could potentially work. And also across different algorithmic approaches. Right, if you think about AI more broadly, it's not just neural networks. And I realize that's shocking to the audience here, but there are other things, right? Knowledge graphs, other regression algorithms, even intuitive representations of knowledge, if you're gonna be very, very old school, some of that stuff still works. This is a representation that'll cross all those different algorithms, and of course, neural networks. There is a constraint, though, if we think about information theory. You need good approximations to what should be formally the optimal in terms of the framework. We think about information theory, it's usually about formal coding in formal systems. These real environments are a lot messier, right? So you're always going to be dealing with approximations, and some of your assumptions may not hold if you're trying to prove things in a rigorous sense about what this representation can actually do. Okay, number 5, robustness to novelty versus novelty detection and characterization. As I pointed out, there is a huge literature on novelty detection through anomaly detection. But it's not inherently useful by itself, right? It's like, fine, we detected it, but as I pointed out, if you're always, or not always, but most of the time you're detecting nuisance novelties that are true novelties, but don't impact agent performance, that's not great. So that means you need some way to characterize these novelties to sort all of this out. And that means you need some regret calculation in your agent to do this. Novelty adaptation then means an agent uses novel information to adjust its decision-making process or as a conditioning agent to ignore it, but not factoring in those nuisance novelties, right? You throw those away, you found the salient novelties you're actually interested in, put that back into your agent. There are different strategies for doing this. And again, this is where you sort of break domain independence, or at least this is what we found to be useful in the DARPA Ceylon program. But again, there were questions about the domain independence aspect of this. So the strategy for perceptual domains, number one, you're going to have a feature extraction via a neural network. Number two, novelty detection using extracted features. Three, you're going to use a clustering algorithm over novel features to identify new categories of novelty. That's your characterization process. Four, you're going to incrementally learn to incorporate this new type of novelty back into the model. Now, the process isn't altogether dissimilar for interactive agents in some activity domain, but there are some differences. Number one, the agent is going to sense information from the environment. Number two, the novelty detection using sensed information is going to take place. Number three, that detected novelty has to be characterized in some way. And then four is the key distinction, right? The agent's plan is revised to incorporate the novelty. All right, another big aspect of this, risk-based reasoning. Novelty detection carries the risk of being too insensitive to hard to detect instances of novelty, or being overly sensitive to all instances of novelty, leading to this problem I keep harping on, right? Nuisance novelty. So I think this notion of regret is a really powerful one, right? Especially right the training process, if you're trying to anticipate, right, the impact of this novelty on future states. And then finally, like checking it, through like a loss formulation, that's going to be really, really insightful, right? As you try to manage these novelties. If the regret is quite low, you're going to learn what these nuisance novelties are quite quickly, right? For whatever your task is, because they're not really impacting the agent in the future. If the regret is extremely high, oh, I need to incrementally learn this novelty because it's really impacting agent performance in the future. So building that in, I think it's something that we typically don't do in these algorithms, but it's something that I think is really key for more successful agent behavior. Okay, to wrap up, let's just talk briefly about the evaluation of these agents. There are two open issues here. Number one, the spectrum of partial knowledge the system designer has about novelty. This is a general problem in AI research, right? Evaluations may leak information. If you're trying to brute force the problem, you may have sucked up some novelties, right, that are in the evaluation unintentionally, or shame on you if you're cheating intentionally. This comes up quite a bit. In fact, we saw this within the Ceylon program with like large vision language models like CLIP, right? In some cases, right, like we can't go and look at all of the training data by hand. And in some cases, these novelties, right, are very subtle, right? And so they're going to be missed even if you did a large-scale manual inspection. So that makes this really dangerous, right? Because you may think you have a really like good agent in terms of its performance, but it's really cheating on all of this stuff, right? That we thought was novel at evaluation time, that was actually in the training data set, right? So you need a really strict firewall. One thing I think which is nice if you're doing these activity domains that are like in simulation, you have a lot more control over the environment, right? So the chance of unintentional leakage is pretty low. That is not the case with traditional computer vision data sets, right? Where we're sort of blindly collecting data, having people label them, right? We know there's some inherent noise in there. And again, if we're thinking about latent novelties, especially nuisance novelties, right? There could be a whole lot going on there, which is an issue. So there are some leak mitigation strategies. Number one, have a sufficiently large validation set of data for the novelty detector to be trained with novelties that do not occur in the testing set for debugging purposes. Number two, clearly describe everything considered to be known. This can be especially difficult with perception domains, but is crucial since the problem becomes underdefined otherwise, making it impossible to tell the difference between nuisance novelty and managed novelty, right? The novelties we care about. During the creation of the novelty detector, ensure that the system is defined by looking for novelty rather than guessing a predefined set of potential novel states. So that is a risk in these interactive domains. I will just anticipate all of the possible states and brute force the problem. You can actually do that with really simple domains like part-1. More expansive virtual environments though, right? I think like a self-driving car simulator, that's not going to be as easy. And then finally, ensure the problem space of potential novelties is large enough that it would be impossible to hand code most of the novel states. Again, that's sort of like the human brute force approach. All right, one more here in terms of open issues, the lack of measures specific to open world learning. I pointed out earlier that the metrics that we find most commonly in the literature are pretty inadequate alone to assess the success of open world learning, right? Accuracy, precision, recall, F1, AUC, MCC. These are basically all limited to classification performance, right? I already said there's this characterization piece that's really hard to figure out metrics-wise. There's more when we think about the performance of incremental learning, all these different things. Also, I think really important, something we don't do enough in computer vision, measuring the uncertainty of these systems. What's really fascinating when you think about uncertainty and novelty, in many cases, the uncertainty of the model is quite high when it sees something new because it's something new, right? That's a really like diagnostic measure, right? But we're not looking at that when it comes to evaluation. And then finally, domain-independent measures for estimating the complexity level of the domain also provides a way to compare different domains, right? Which is pretty interesting. As I mentioned, right, just sort of in an informal way, some domains are really simple, like part-1. Some are really sophisticated, right? Like a self-driving car simulator, right? There's a range of that. It'd be nice to actually put some numbers to those. So we do this in a more rigorous way. All right, I'll wrap up here. I just want to acknowledge my collaborators on this work. Steve Cruz, who's a postdoc in my lab at Notre Dame, Chris Funk at Kitware, who was on our team for the DARPA Ceylon program, and Katerina Doctor from the Naval Research Laboratory, who was running parts of the DARPA Ceylon program with respect to evaluation, who helped us sort of formulate these open issues. If I have any time left, I'm happy to take a question or two. It looks like I do. Woo. Questions from the audience? Surely there's a question. I know it's early and I'm like the second talk in this workshop. Everybody's still caffeinating. Yes, yeah.
As you mentioned, Clip is trained on tons and tons of data, we don't know what's in it, and your solution is have a sufficiently large validation set. So how does that actually solve the issue? Because we don't necessarily.
Yeah. Let me add another clarification. I think the warning I would give everybody: don't use Clip out of the box. Like you're gonna have to retrain these things, right, with like a better curated data set. And again, this is true of a lot of like the sort of like foundation model, large model, right? It's just they're a huge headache to work with in open world evaluation, just because again, you don't know what's in there. So I'd say you have a much better handle on this if you do it from scratch, but there are still pitfalls, right? Because there's just so much data, and again, especially if you're thinking about nuisance novelties, things you didn't anticipate that are in there. That's going to be a factor. Again, not as much of an issue when you're dealing with an interactive environment where you control like the game engine. But yeah, this is a really important point. Anything else? Yes.
First, thank you for your good presentation here. My question will be, if we jump out of the abstract definition of the novelty, we look at some real cases, for example, the open world detection, then we need to figuring out the granularity of the novelty. Because if you really take, for example, this building, you could take it as a whole, and you could take it as a piece of this wall, this windows. You could also take it as a piece of the material, and this kind of stuff you could always divide it into the small pieces and what to end. And if you always do the incremental learning, then the capacity of the model is limited. Then how?
Yeah, this is a great question. It comes back to flip back all the way here. This idea of a hierarchy, right? As I mentioned, this was just one first cut of the hierarchy. I agree. This could be an enormous hierarchy, and much of what's in the hierarchy is irrelevant for the task, right? So this comes back to my point on nuisance novelty. I think this is one of, again, the more underappreciated aspects of this problem, managing that. I think in most cases, right, you need an agent that knows that those really fine-grained distinctions are not impacting task performance. That could be through its regret formulation, and it's simply ignoring them, even though they are truly novel and exist in the hierarchy in some sense, right? But that's not easy, right? That's a really tough situation.
I think this back to this relation of novelty, because we not only want to find it, but we also need to figure out what is really important for us. So
Yeah. Great. All right. I'll turn it over to our next speaker. Thank you, everybody.
Let's thank the speaker again. All right, it looks like we need a bigger room. All right, I am very happy to introduce our next speaker, Deva Ramadan, who has won basically every computer vision award under the sun, including the Mara Prize, Pascal Vios Lifetime Achievement Award, Longan Higgins Prize, Best Paper Awards at CBPR 19, CCV 20, ICCV 21. And over the years, I've had the opportunity to have many interesting discussions with Deva about open world perception. And he has a very unique perspective that we will see today in his talk, Open World Learning in the Era of Multimodal Foundation Models. And with that, I'll hand it off to Deva.
Okay, thank you. It's sort of nice to get introduced by your own student. Okay, so let me kind of motivate my own sort of foray into this open world setting is when I arrived at CMU in 2015, I had a conversation with Andrew Moore, who just recently returned at that point to academia from Google. And at that point, that was right around the deep learning revolution. And I think he was probably the one person in the world training more machine learning models than anyone else. And he had this statement that always stuck with me. He said, I spent most that. Okay, I'm going to say more. Hide. Okay. So first off, there's a continual learning workshop happening right now. And so one of the things that frustrated us when we first looked at this is that the data sets were all very toy, sort of a continual learning MNIST. And if this is really such a big problem that you're sort of faced with it, even if you don't want to in the real world, we shouldn't have to really invent a setup for this. The data should just be screaming at us. So the first thing we tried was we went to Yahoo Flickr 100 million. We assembled a data set of different categories of objects that we thought actually interestingly evolved over a span of 10 years. So this data is timestamped. There's a wonderful talk in one of the workshops yesterday by Dima on the fact that 10 years ago, we all had Walkmans, and now you don't see that anymore. So even the radios that we've been using have changed from before to now. So we put together a benchmark, the lead student involved with the CQ, and he sort of put a lot of blood, sweat, and tears into this. A whole slew of categories. I think we even talked about this in previous iterations of the workshop. And let me just tell you some sort of take-home messages. First was that one of the reasons I guess we became disillusioned in this space was that the setup for continual learning felt a little bit artificial to me. The traditional setup was really sort of on the left-hand side, where you got data that evolved over time, but your train and test data both evolved. And the problem with this is this doesn't address the problem that Andrew Moore said he dealt with, which was domain shift. So the right-hand side is more of a realistic setting where the new data comes, the new data is shifted because it pertains to this year. Now you see, this year's models of iPhones versus before you just saw flip phones. And so what's kind of interesting about this is that once you test on this data, so today's test data next year will become your training set because you'll get a new fresh fire hose of data arriving from this continual stream. And one nice sort of aspect of this is that you can sort of theoretically avoid overfitting because essentially once you test on a data set, At some level, once you learn that transformers work better than convolutional networks, you've done model selection on this test set and you've somehow polluted it. And so what this is saying is that in a true continual learning setup, that should become your train set and you should get new fresh data next year. But one more sort of take home from the this sort of large scale effort we put is that it felt even more important to emphasize the role of unlabeled data. So this fire hose of data is coming in, and you can't really afford to label all of it. You actually only afford to have a smidgen of this. And so we found is that just like continual learning algorithms that really leverage unlabeled data did much better. And in fact, there's something wrong with this picture, because if I can only afford to label a little bit data for training, I can't really afford to test on all this data. So in fact, there's another problem that we have, is that even testing, we should think about is we evaluate models with a little bit of labeled data and a whole bunch of unlabeled. And so just like we have this problem of like semi-supervised learning, I think there's analogous difficulty of semi-supervised validation. So we had this old paper on this, and it turns out you can apply a lot of similar ideas from the semi-supervised learning, but there is some wrinkles there. Okay. But now I want to sort of zoom out. And so this suggests that the role of unlabeled data is really important. And that's no surprise. We live in the foundational self-supervised era. Oh, let me sort of, okay, let me just sort of skip this then. The thing that kind of kept me up was this, this perspective of, if the real challenge here is really about shifting kind of distributions, then we actually look at this as a community using different nomenclature. Sometimes we'll use the term domain adaptation in addition to continual learning. And I think one of the world experts on this is Kate Senko, and we were having this conversation with her at the workshop, where she held a whole bunch of like domain adaptation benchmarks where sort of, you know, her group was working on innovations of training models that'd be easier to domain adapt. But her take-home statement is that it was sobering to see just how well scaled-up models performed compared to models deliberately designed to adapt. And so this is also not surprising. Like in some sense, the OpenAI did not make a bet on domain adaptation, did not make a bet on continual learning. They made a bet on scale, and it seemed like that was the right bet at that time. So the perspective that I want to think about open world learning is that I think it's important to think about how do we characterize open world learning in the context of foundational models. So is Walt still here? Okay, well, so I'm curious here to think about this. So I would make the claim that like we need to have a formulation of the problem that lets these big behemoth models enter into the conversation. Because if we say that they can't because we don't know what you were trained on, then it seems like somehow we're dead in the water, because we know it feels like one of the biggest tools we have for generalization is scale, and we need to be able to like ask about it. So there's a wonderful exchange with Bharath and Jitendra that stuck with me as well. So you brought up this question in one of these workshops, like, okay, if we don't know what models are trained on, how can we test them? And Jitendra's answer was perfect. He said, well, that means we have to rethink the way that we frame the problem. So my claim is we need to rethink, 100% agree, we have to rethink the way that we frame. We should not allow that. We should allow it, but it's on us to sort of figure out a setting that allows those things to come into play. So what is the right setting to think about open world, few shot learning with foundational models? And the starting point for us is, well, did these models really solve vision? So this is an autonomous vehicle data set where what we did here is we ran an open world detector, GLIP, I think, or DEDIC. But here's the results of this. And what's kind of interesting is that this is actually, this does not score well according to the ground truth. And it turns out that the way that this data was annotated was the bicycle bounding box included the person and the bicycle, and the truck just included the front cab of this tractor trailer and not the trailer portion. So it feels like there's a disconnect between the way these data sets were annotated and what, I don't know, GPT for vision or these foundation models think a truck or bicycle should be. So I guess any guess as to why this exists? Well, what's kind of interesting is that you can pinpoint exactly why this exists, and that is there's an instructions protocol for this data set where the annotators were instructed to label bicycles as only containing a bounding box that only contains the bicycle and not the person. So this is very literally what annotators were told to annotate. And what's kind of confusing is that this is actually a different definition than what Waymo thinks is a bicycle. So according to Waymo's definition, you should not annotate a bicycle that has no person on it. So it's the exact opposite. So at some level, it seems like if we don't agree on the definition of bicycle, how do we expect a foundational model to know what we mean when we say bicycle? And in fact, I think it gets even worse than this. There's been sort of well-known analysis of like errors in analysis of errors in data sets, in particular high-stakes data sets like autonomous vehicle benchmarks, where folks have analyzed, oh, these benchmarks are missing ground truth annotations, and this is really dangerous. This means that there's safety critical systems that are being trained with flawed data. And there's sort of an enormous, like a sort of an interesting Twitter response that said, actually, no, the labeling policy told annotators not to label cars that were not on the drivable surface. If you're in a parking lot, don't annotate them. Somehow it feels like we have to come to grips with this. So clearly there's directives from on high in the White House. So we need trustworthy artificial intelligence. And one of the things about how we can build trust in what a system does is we have to understand what it was told to do. Something we've been thinking about is thinking about instructions as a technical artifact. And I think instructions are incredibly interesting. It's almost like how a stakeholder explains to an annotator what they want. And oftentimes it's done in a very deliberate multimodal way. We give textual descriptions of what we mean by barrier. These are the actual instructions for this data set. We give visual examples, and the visual examples span different things. Sometimes we show prototypes. This is a really nice, clean barrier. Sometimes we show partially occluded barriers. We show corner cases because we want to make sure the annotator knows you should also annotate this. And sometimes, this is cool, you show what a barrier is not, because annotators get confused by that. So, and sometimes you just get really weird descriptions of classes. So one of the classes you have to annotate is debris. If I asked you to annotate debris in images, I think you'd have a really hard time. You kind of need to see what examples mean and need to see this. It seems very helpful to see this description and also see these visual examples. So what I claim is that I remember this time in the self-driving space myself, that oftentimes, anytime you're involved in a labeling effort, there's this incredibly complex and laborious conversation that happens between the stakeholders and annotators, where they keep saying, is a reflection of a person, should I label that as a person? If I have a construction crane that's mounted to the ground, is that a vehicle? And you keep refining a policy of what it means to be a person, what it means to be a construction crane. And here's a sort of maybe a controversial claim. Maybe that actual policy is more valuable than the annotations themselves. Because it takes money to build that policy, because you have to iterate, you have to have a conversation. So the claim that I want to make is that we should almost treat labeling instructions as a first-class citizen. It's part of a data set, and it's a vital part of how a model gets trained and oriented. And if you look at work from the fairness community, data sets for data sheets was a landmark paper. It falls a little bit short of saying we should also release annotation instructions. So in fact, we've tried to get annotation instructions. Some of them have just been forgotten in the test through the annals of time. I don't know what the instructions for ImageNet actually were, and which is kind of a problem, because there was a fantastic piece of work by Ben Recht where he collected ImageNet v2 to kind of verify how well does it actually, have we been overfitting or do we actually generalize? And in order to collect a v2, it would have been really great if we just had the exact same instructions and you could just run them again. So even for like policing ourselves and doing due diligence, it's nice to have these things as historical artifacts. Okay. And what I claim, though, is that this is actually maybe a really nice way to think about few shot recognition. What I'm showing here are 6 examples that try to describe a class or a concept. And there's positive examples, negative examples. And in fact, this is what Anish and Nihar and Shu have put together as one of the benchmark competitions associated with the workshop. A way of thinking about, one claim is you can think about few shot recognition in the foundational age as almost multimodal fine tuning of you have a foundational model and it might think it has its own definition of what a truck or a bicycle is, and I want to kind of adapt it to what I mean when I say truck or bicycle. And I can actually use the exact same artifacts that we use to adapt each other when we explain to an annotator. And now, what's also, I think, kind of interesting is that you could think about this as almost just like multimodal prompting. But rather than sort of picking random examples, these have been prompt engineered, because that's how it's been engineered through this laborious process of how we explain to each other what this concept means. So this is one sort of hypothesis for how to think about open world learning. We really think about it in terms of adaptation or alignment of these models to the particular thing we want them to do. We don't really have a good word for this. We welcome any ideas. Like right now, we're calling this benchmark a foundational few shot. And I don't know, I almost feel like it should be called multimodal few shot. Okay, and this is work that Anish and Nihar will talk about later today. Hey guys. And I think there's been, so I've been involved in various benchmark competitions, and one hallmark for me for success is that if the winning entry does much better than the baseline, and that's true here. So something interesting happened when we set this up and challenged people to attack this problem. They came up with interesting solutions. So I encourage you guys to listen to that later on today. Oh, and so my bet, now that we think about how should we kind of adapt a model to what we want it to do, we can do it via prompting, we can do it via in-context learning, we can do retrieval augmented generation, we can do fine-tuning, grading updates. There's all this kind of new tools that we have. My own bet that I've told my students a lot is that I think it's just going to be in-context prompting, but I lost that bet. So if you look at the winning results here, they actually do some real gradient-based fine-tuning. Okay. Oh, and I'll show like one, do you know how much time I have? Okay. I'll show one kind of fun example of one particular approach of fine-tuning a multimodal model. That's really simple and kind of motivated by, maybe I should first kind of, even though I sort of motivated this multimodal adaptation task from a practical perspective, I think there's a lot of cognitive motivation for this. So in the cognitive development literature, there's evidence to suggest that when you teach the concepts to children, it really helps to give multimodal cues. You show visual examples and you explain what you mean. And it's remarkable to have both of those different modalities. In fact, in neuroscience, there's a lot of evidence to suggest that when you say a particular word and when you see that object, the same neuron fires. So it's sort of interesting to think about multimodal representations that are biologically motivated. And of course, we use them quite a bit, things like clip. And the intuition I want to throw out is that here's a really simple multimodal fine-tuning algorithm that leverages this kind of cross-modal space that clip has. So importantly, sorry, here. Okay, it says audio encoder, it should be text encoder. But what I'm saying is pretend you're trying to solve a two-shot problem where you're given two examples of a class, but you also have a class description. And normally, if you're going to train a few-shot classifier, you would just take these two examples, unless you would just do linear programming. You would extract a 512-dimensional feature associated with the two examples and feed that into a classifier. Let me remove this. Okay, feed that into a classifier. But since I'm trying to sort of emphasize this multimodal perspective, we also have a textual description of the class. At the very least, we have the class name. But maybe it's even more. Maybe it's one of these rich instructions. But I can take any of that text, push it through my clip text encoder. I also get a 512-dimensional vector. So now I can think about learning my linear probe classifier using 3 examples instead of 2. And as you might imagine, this is going to help because 3 examples is way more than 2. I've doubled or increased my data set by 50%. And so just by training a linear classifier on top of these 3 examples, you can do much better. And this is in contrast, I think, much more complicated prompting models and prompting techniques that sometimes take half a day to train versus this thing literally takes seconds because you're just training a linear classifier on pre-extracted features. But the features are actually using different modality encoders, your text encoder from clip and your vision encoder from clip. Because they always map your data points to the same space, you can just treat them as 3 examples. So a kind of a fun artifact of this is that this works for any kind of modalities. So we tried this on a data set of vision and audio examples, so something called ImageNet with sound. So there you can have image classes, let's say of dog, that's one class. You also have audio clips of dogs barking. And just as we showed before, training with 3 examples is always better than 2, the same holds here. You can train with these 3 examples that are multimodal. You get a linear classifier, a linear flow classifier that works better just because it's been trained with more data. And that linear classifier can be run on any one modality at test time. It can be run on audio stuff, audio clips, and visual examples. So what's cool about this is that what this means is that actually listening to a dog bark helps you do better at visual classification of dogs, which is sort of a cool result. It's sort of really leading into this multimodal encoding. Okay. All right. Let's say, this is just sort of a shameless advertisement for ZK will present a poster this week on if we're leaning into this space of really leveraging text and visual examples to do adaptation. We know that unknowingly these models are really sensitive to the textual prompts that we give. And so this is why I've heard this derived as we don't want to just resort to prompt engineering. That's a hack. One of the things we've been looking at is, can you actually automate prompt engineering by using another LLM? And it turns out you can. So language models as black box optimizers for vision language tasks. So the idea is that you can actually give it, and maybe you have your few shot training set, and you can say, give me a prompt that will help me learn visual classifiers that will correctly classify my few shot examples. And then you can give it feedback about what prompts worked well and what prompts didn't. And it can actually do a form of hill climbing. This is one of these wacky things that chat models can do. But the end result of this is we can learn prompts, or not we, the system can learn prompts that are actually better than prompt engineered results that we've seen. And what's kind of neat is it actually learns prompts. We can evaluate this on ImageNet or other target data sets. It can actually learn prompts that sort of describe what the data is. It kind of makes sense in this reasonable way. So if you're processing Caltech images that tend to have centered objects, if you give it a textual prompt that's not just a dog, but it's an image of a dog with a blurred background that emphasizes the subject, you'll do better on Caltech. And so you can discover that automatically. You can apply sort of similar things for increasing the accuracy of DALL-E 3 image generation or prompt inversion. So we actually are using this code quite a bit to avoid prompt engineering ourselves for all of our projects. So I encourage folks to try this out. Okay, in the last few minutes, I want to talk about how to extend such foundational knowledge to multiple modalities. So the argument that I want to make once again is that we kind of need to embrace this enormous, massive knowledge source that exists out there and figure out how to use it. And one of the ways that I want to exploit this is that I want to bring it to other modalities that we don't have all this massive knowledge for. So I talked about one method already with this cross-modal linear probing. We have a couple of other projects in collaboration with folks as well that try to bring this knowledge to LiDAR. So in the space of autonomous vehicles, LiDAR is a very important sensor, but right now, I don't think we'll ever have the amount of data in LiDAR that we have for images. And so how can we best kind of leverage foundational models for images to help us improve processing of a different modality that we don't have foundational knowledge for? And it turns out there's actually a really kind of simple philosophy that we've seen work fairly well. And that is, assume you have unlabeled data that is across modalities, so cameras and LiDAR. So this you can get just by mounting a camera next to a depth sensor. We all have one right here, a multimodal sensor. The black thing is a LiDAR. So my claim is it's easy to get multimodal data. We have lots of foundational image data, and maybe I should say foundational image models that are encoded in the models, but we don't have anything like this for LiDARs. But how do we kind of transfer it? And so one simple approach is we take these foundational image models, we can run SAM, DEDIC, or any of these other things on the images. And then using the aligned LiDAR, we try to unproject into labels that we have for instances into the LiDAR point cloud. And this is relatively straightforward because we have knowledge of where all the points, these LiDAR points project to these image pixels. We can use extra knowledge of maps and the fact that 3D objects tend to be aligned to driving directions. But once we do that, now we can get pseudo labels for 3D annotations And now we just interpret this as pseudo-labeled multimodal data. And from this, we can then train, actually, oh, I should have started with, we can train a LiDAR 3D detector. That's the top one. We can train a multimodal 3D detector. And what's also kind of interesting is we can actually distill this back to the image domain and train a RGB 3D detector, now that you have this aligned data. And so we have a couple of papers, including segment anything in LiDAR. Aliosh is there, that's his baby. And then we have some variant of this that looks at 3D detection. And then segment anything in LiDAR does one remarkable step further, which is instead of actually using annotated cuboids, it preserves a clip embedding. And what that allows you to do is learn a representation just for LiDAR that allows you to type in any bits of text and then find objects that correspond to trash cans or debris or any of these other complex things that I hinted at before. And there's some results from the detection side as well. Where here we've also focused on RGB only detectors or even multimodal detectors where you have access to both modalities of test on. Okay, let me skip this for the moment. Okay, and actually maybe I'll kind of call it here. So this was sort of the, let's say a take-home summary. So this was all motivated by thinking about this problem of domain shift. What happens when your test data doesn't look like your training set? And so while that really prompted the problem, at least for me personally, looking at domain adaptation and continual learning, somehow I got a bit disillusioned from that perspective when we saw all this incredible innovation just by brute force scale. And so I want to think about still this problem of how do we adapt to our particular test scenario using these massively trained models. And so I think these multimodal instructions are a nice way to think about it. Because at the very least, that's the way we talk to each other. That's the way we instruct our kids what these new concepts are. And then finally, one of the aspects of doing sort of multimodal learning is that being able to transfer information across modalities. And here, I think the assumption is always going to be that the elephant in the room is we have so much knowledge for images that will always dwarf any amount of data that we'll have for LiDAR, for audio, for tactile. And we have to think about how to transfer this this incredible knowledge source to the other modalities. Okay, and I will end there. Thanks. Yes.
I think regarding the second one that you mentioned, the instructions for actually creating good data sets. This is a problem that we face in the industry quite a bit. We have a team of 1,000+ freelancers working as annotators there. We got a lot of domain shift as well as tricky annotation instructions. But in your approach, what you're mentioning, right, basically treating it as a prompt engineering problem by itself.
Yeah.
I think one thing that we're missing here is the continuous feedback loop, because for like the analogy that you took, right, you have to, how do you tell a kid about how to go about describing the scene, right? It's not a one-shot learning. It is always a continuous feedback. It may be a few feedback steps or a long series of feedback steps depending on coaching versus kind of one-sided instructions. But do you think that for continuous or for more complex problems where real-world scenarios have to be captured, this prompt engineering approach can be kind of created through a feedback loop, which can continuously kind of keep improving?
Yeah, you know, I agree 100%. So in fact, the analogy I want to make is like, I definitely saw that as a conversation between stakeholders and annotators. And that conversation was incredibly laborious.
Yeah.
It took a long time and it was backbreaking. And then I almost feel like, you know, maybe in the future, instead of having conversations with the annotators, we will have those conversations with chatbots, which that's what they enable. They enable chatting with history. So I actually think that's very doable right now. Yeah, so I think it actually fits in very well into current technology.
So very nice spot. So when you're developing a model, for example, you're trying to debug it against the benchmark, and I think what you described is basically if your model actually aligns better with the instruction they learn that it'll perform better, which doesn't mean that it'll actually perform better when you put it on like application yourself. I think there's a coming from the like lack of instruction. And I mean, how should we interpret all those benchmarks? Can you trust them or like from the application development perspective? I think there's different
Yeah. So I don't have a great answer. So in other words, what you're saying is it could be that the stakeholders are wrong. Because ultimately what you really want is to, I don't know, in the perspective of a self-driving car, I want to build a self-driving car. I don't want to just make someone happy that has labeled, I think a bicycle should include a person. It's kind of an arbitrary distinction. So I think I don't have a great answer for you there. The angle that I want to take is that at some level, when it comes to perhaps these high risk applications, we need to have some visibility into what we think the model can do. This is sort of the transparency and trust argument for AI. You know, the White House dictate. And so for that, I think it's almost like instead of trying to build trust in the model, we almost build trust in the instructions given to the model. So I don't know how to ensure that, but I think that's going to be part of the equation. And right now, it seems to not be. Like right now, there's a lot of the instructions are sort of lost in the history of time. And I really like what you said too. Like sometimes this is maybe a bold claim. I almost feel like their ads are more important than the actual data annotation themselves.
Basically, the process of passing on that information is actually much more critical than the annotation itself.
Which is fascinating because then that's not how we talk about data as well. We talk about data and labels. We don't talk about this other thing. Go for it.
So one is so this idea of using instructions. It also happens back a little bit to some of the older work in the classical, well, now classical yes, of zero-shot learning. So I think some of Nakata's work included like the combination of the text would be descriptions in that kind of like attribute descriptions of words and so forth in the reduction images. And in the fine-grained characterization images, it's sort of very common because field guides often have big textual descriptions.
Got it.
But the question I wanted to ask actually was about, so I guess if I was to go back to the original question of like open world,
Yeah.
do you still think that there will be a distinction when we are adapting between sort of concepts that the model has seen in some way in training versus not? Is that something that is worth testing or it's harder to product?
Yeah, okay. I can tell you, and this may be the wrong way, but this is the best way I would think about this now is that I want to come up with a framing of it where I don't have to know what it was trained on because I want to let things that have been trained privately to enter in the conversation. So if that's the case, then I don't want to shackle handcuffs on what you're allowed to train on. But then I want to argue that it's my due diligence as a benchmarker or evaluator to make sure that, for example, I can go out and take pictures right now. And if I go out and take pictures right now, I know those don't exist on the internet. There might be very similar ones, but at least those don't because I just took them right now. I can take it, I can put them on a computer that is, insulated from the internet. And then I can say, this is my validation set. And so I would rather sort of take it, put the onus on the collection of the validation rather than the way that it's trained. Go for it.
So I guess this is also a benchmarking question, but suppose I want to set up a benchmark with a multimodal prompt. Do I take the prompt that's been engineered for human communication on a particular task, or do I take one that you've done hill climbing with respect to a particular model? So ideally, I would like this interactive setting, but of course, that I also don't know how to set up a consistent kind of evaluation that uses interactive, short of just asking lots of humans to evaluate.
Totally. That's exactly the right question. I don't have any answer for that, but that's exactly what we're sort of wrestling with now. Like, what is the right way to formalize it or set it? I mean, one nice thing that I do like is that it seems interesting that like instructions we have right now are already engineered, so might as well like start with that. It's been engineered so that we, in a way that we think helps communicate to each other what we mean by something, and then we can see if we could do better. So it could be that like maybe they haven't been engineered well. maybe if we had just said the right thing to the annotator, we would have gotten even better quality than what we did historically. Like I remember this artifact when we were looking at the cocoa annotation. There was like this cultural issue. We had a lot of annotators from China and India, and they didn't quite know if a hot dog was a sandwich or not. And so that was one of those things that came out of this conversational process where we had to refine the instruction to say that. And so my guess is probably if we worded things a different way and gave different visual examples, we would have gotten higher quality. And so, so hopefully we can start with what exists there and then actually see if we can optimize. But then in order to optimize, you need to have some data. I guess that would be the few shot examples like that's what we technically hill climbed on. Yeah, go for it.
Just because you definitely see the value. There's a ton of stuff with images, there's a ton of stuff with text, but it seems like most of the power that we come from multimodal is the stuff that's unique to whatever domain. So think about audio, doing stuff that isn't in the scene by definition. How do you see a path forward?
Yeah. So I don't have a great example for the audio setting, but like, let me give you an example from the one-shot setting. So if I give you an image of a purple cowboy hat, and I say, find me one-shot examples that look like this, and I just give you the visual image, I don't think you know what I'm asking. I might be asking you to look for hats, I might be asking you to look for cowboy hats, maybe asking you to look for purple cowboy hats, and just a little bit of text. There's a dramatically helpful in resolving that ambiguity. I think that's one of those reasons why, when we sort of explain things, having the different modalities is oftentimes helpful. So it's definitely the case of like sometimes, like in that case, that bit of text is even more useful than another visual example, because it totally explains what it is you're trying to find. So my intuition is that things like this would exist for audio and other modalities as well. I haven't really thought about that. But I think that'd be cool if somehow like the sum of the modalities is more than the parts.
Can you put it this way that it is easier to actually state a rule or state a exception in text rather than in images, right? You can label an image, but you can't really express whether, so the bicycle example, right? What to exclude, what to include, or similarly the hat example. You have to label 1,000 images to basically kind of make an understanding that you are supposed to only label cowboy hats or purple hats, or whatever, but you could just write it in the text, stating rules in text.
Yeah. So I could imagine, like, I think an interesting space maybe to answer Charles's question as well is thinking about this maybe not just wholly with text, but a bit more programmatically. Jarek was saying this. So for example, like finding not purple cowboy hats. If you just put that in text, like there's a lot of text encoders that get confused by that one word not. But I could easily kind of algorithmically code something like how purple is it, and then downweight the score based on that. Like I almost algorithmically change sort of clip cosine similarity. And so I think programming some of this is really natural. And so that's one of the things I also was super excited about the instructions, that they naturally include negative examples. Like in few shot, we normally don't, it doesn't enter in the story, but once we think about how we talk to each other, it's very much there. Okay.
Thanks.
issue. Is everything okay on the Zoom side? Great. Hey, how's it going? Yeah, it's like oh. Yeah, no, I did, yeah, thanks a lot. Thank you so much. All credit to my students. For folks over Zoom, can you did this fix the problem? Are you seeing the right thing now? Ah, great. Okay. Thank you. Thank you for letting me know. Yeah, sure, sure. And it's I think it's a 40-minute block.
Yes.
Okay. Okay, great.
Actually, let me just double check. If you don't wanna. We were good to go until 10:55. Yeah, 10:55.
Okay, great, great, great. I'll try to finish for that.
All right, thank you everyone for joining us. Let's get started. Our next speaker is Andrew Owens from the University of Michigan, who is this professor there. And he's done a ton of cool work in multimodal learning, learning from video, image forensics. Some of you may be familiar with his long-running workshop, Sight and Sound, which has been in its 7th year. And if you're frequenting on academic machine learning Twitter, maybe you've seen some cool visuals of visual anagrams, and all these projects. But today, Andrew will be talking about learning multimodal models of the physical world and I'm very excited to see what he's been cooking up at the University of Michigan. Please, take
Thank
away.
you, thank you so much for the very kind introduction. I'm really excited to be here, and thank you so much for inviting me. So we still get a lot of our supervision today from humans. In the past, some of the information we get would be from really specific things like labels or semantic segmentations or scene categories. But as we've seen in the last few talks, increasingly we're relying on language-based supervision. There's been this move toward learning from correspondences between vision and text. And while it might feel like this data is really abundant and it's free, at the end of the day, you still need humans to provide you with this data. And there's a lot of limitations to the information these humans might provide. For example, it can be relatively high-level information that in some ways may be imprecise. And maybe more subtly, you can't learn from this kind of data autonomously. Like if you imagine a robot that learns from language, and the only way that it can learn about the world is as a phone home and ask a human to provide it with instructions, it's really going to be a very limited system. And so if we're building these so-called foundation models that we're using to build for other computer vision tasks, you might ask whether we're building them on shaky foundations. On the one hand, you have these sort of high-level forms of supervision, like labels and language, and the other major form of supervision is just the raw images themselves that you learn from self-supervision. But I think there's kind of this missing middle of supervision that comes from other sensors. Like Deva mentioned LiDAR as one, but there are also others that are maybe more familiar to us, like touch and sound. And so the work I'm going to talk today is about learning from this sensory supervision that comes from other sensors. And in particular, I'll be talking about two different ways that you can learn from this kinds of data using 3D constraints to learn from tactile signals and using a kind of analogy reasoning to learn from audio. So one of the constraints that I think these other that we have on these existing vision systems is they have a lot of trouble understanding kind of the nuances of the physical world. If you consider like our very best reconstructions of a scene, we might have this kind of shell of the scene. We can't tell that beneath the surface of this concrete, it's actually this really rough, complex microgeometry, or that it's a rigid surface. If I put my hand on it, it's not going to move. Instead, we just have this kind of like empty shell that we get from say a Nerf. And also what's missing beyond microgeometry is this notion of physical interaction. Like if we see this dirt, we as humans know what will happen if you manipulate it. It's soft, it's crumbly. If you put your hand in it, it will deform. But it's challenging to learn that information, except in a very high level way from signals like language right now. And so how do you connect vision with this sense of touch? And we wanted to create models that connect images with their corresponding tactile signals. But unlike in other modalities, it's a little bit less clear how you do this with touch. The sensors are less standardized. It's not as obvious how you collect the data, and not clear how you define the models. And so we started out with this, so our group has been working on this for several years. And as just a point of background, we were relying on these recent touch sensors called vision-based touch sensors that you might have seen before, that are really enabling some really interesting applications of touch. And if you haven't seen these before, there are sensors like GelSight or Digit that essentially convert touch sensing into a tactile sensing problem. You're going to create an image like this one here that captures what you're touching. So in this case, we're touching an avocado, and you can see the ridges of the avocado in this video, and the hardness of the avocado is apparent in its the amount of deformation that you're seeing in the video. And in fact, you could like predict if it's a ripe or pre-ripened or before ripe avocado this way. And here's how these work. You're just going to take a commodity camera, put a piece of gel on it, on the lens, And then when you push the sensor into an object, the object deforms the gel, and then you see a video of the deforming gel in the camera. And to make this image a little bit easier to interpret, we can add colored lights that illuminate the gel from many different directions, the same trick you might have seen in photometric stereo. And this is an idea that's originated from Ted Adelson's group and has been really carried a long way by Wenjin Yuan at UIUC. And so we essentially convert this, this touch signal into this video of an illuminated gel that captures shape over time and that you can process with off-the-shelf video understanding. And the work I'm going to present, we're going to use these touch sensors and we're going to exploit the fact that it's under the hood a camera. Okay, so how do you actually collect paired vision and touch data? When I was starting out, I thought a really good way to do this would be to use robots. You just take a robot in a room, you give it all these objects, and you have it repeatedly touch them and record video at the same time. And well, you can do some interesting things with this. Unfortunately, it's very hard to get diverse data. The robot really only sees one thing, the table that it's sitting on. And there's almost this like chicken and egg problem. Like if the robot is able to successfully perceive an object with touch, it probably is already capable of manipulating it to some extent. And so it's hard to learn really like diverse objects and that would be difficult for a robot to autonomously manage. And so there is something though that's much better than robots for this, and that's undergrads. So we can we have this in our later work. We get this team of amazing undergrads, some of whom are now PhD students presenting work at this conference, and we just had them. They just went out and they just collected everything they could with a touch sensor while simultaneously recording egocentric video. And they really took this really far. They went all over. They went to parks. They went to offices. At one point, they got politely told to leave a museum. And you can see these videos here. They have a egocentric video with the corresponding tactile signal. And what you're seeing is this video of this deforming gel. And the changes in the colors convey the microgeometry. And over time, you see how it changes. And really, went all over Ann Arbor, captured roughly 14,000 different tactile signals and 4,000 different object instances. One of these students, Fred Young, is here presenting a paper on Friday on touch sensing as well. And once you have this data, now you can use it in much the same way you can in other areas of multimodal learning. You can do things like learn a joint embedding between vision and touch and distinguish between real visual tactile pairs like this and fake visual tactile pairs like this that are mismatched. And one preliminary experiment with this that I thought was really interesting is that even though we trained this embedding on entirely real data collected by humans, we were able to take the features that we learned and use them for a robotic tactile sensing task, namely some grasp prediction work that we had previously studied. And we found the features we learned outperformed ImageNet features for this task on the touch representation. And well, one preliminary experiment, I think it shows that because you can scale up this procedure and collect more diverse data, more adventurous kinds of data in the world, you can potentially compensate for the mismatch in domain between the robot and the human to some extent. And other things you can do, like the same students, Fred and Jie Ching, they tried to predict images from touch. So you can train a diffusion model to condition it on a sequence of touch signals and generate a corresponding image that might have gone with it. And we have some tricks for getting rid of the hand here. So you can see the real image is in the middle. It's got a hand in it. The generated image is on the right. It looks like other grass with no hand. Here's another example. If you're touching this wood, this is what the model thinks you're pressing. And you can even do other things that have been considered in the language domain, like you can stylize images using touch. So let's say you have this input image of these bumpy rocks, you can restyle it using this touch signal that comes from the smooth surface using SD edit, and we get this result. Like kind of smooth out some of the rough parts of that signal. You can even try crazier things like make this carpet feel more like this tree, and this is what you get. You can clearly, it knows like what's being pressed, but yeah, I'm not really sure what it should do in that case, but it has kind of an interesting result. Okay, so as ambitious as as great as undergrads are at this task, unfortunately, there's a lot of limitations to this approach. And Deva talked about how LiDAR data collection will never be quite as large scale as vision. This is even more extreme because every time there's not like some device that's capturing tons of data passively. In this case, you have to actually physically probe everything that you want to record. You have to manually press all of these different locations at the scene. There's also this more subtle issue of occlusion. If you're touching something, the visual signal won't see exactly what you're touching because the touch sensor will occlude it. And there's also this other issue that it's, at least the way we capture this is very object-centric. There's nothing that tells you how the touch signal relates in two different parts of a scene. And so we wanted to see if we could reduce some of these limitations by putting vision and touch in a shared 3D space. So we'd like to create 3D reconstructions where you can select different locations and estimate what the corresponding touch signal is. And I think these multimodal 3D reconstructions are potentially very useful because they can give models a sense of touch. You can just directly access what the touch signal would be at different locations. They're also potentially useful as sources of paired training data, because if you have paired sight and touch, you can sample arbitrary viewpoints for each touch signal. And I think ultimately what makes me excited about this is the potential to create multimodal environments where you can imagine creating an agent that learns in a visual tactile reconstruction, both what things look like and how they feel. And so this is some work that's being presented here at CVPR on Friday, led by Yiming Dao, also with Fred Yong, Yves Liu, and Antonio Loquercio, who's starting at Penn in the fall. And we wanted to see if we could create what we call tactile augmented radiance field. It's going to be a nerf where you have a sense of touch in many of the locations of the nerf. And so here's how this worked. We wanted to register the touch in 3D and find where it lies within a 3D reconstruction. So the way we did this, we took a selfie stick and put a camera on one end and a touch sensor on the other. And then Yiming just went around and he just pressed the selfie stick on all these different objects and simultaneously recorded both a touch signal and also a visual signal. And now that we have both of these signals, we have a way that we can register the touch in 3D. Because if we can register the location of the visual signal, and we know the relative pose between the vision and touch, then we can chain these two transformations together to figure out where we're pressing things in 3D. But there's also this question: how do you get this signal? How do you get this transformation? How do you get the relative pose between vision and touch? Well, we can take advantage of this fact I mentioned before, which is that these vision-based touch sensors are cameras in disguise. You have this camera and it has some gel on it. And so we can just use tricks from multi-view geometry to find the relative pose between real cameras and touch cameras. So here's how this works. We'd press the touch sensor on a braille board in each scene. Yiming would then manually annotate correspondences between the bumps that we're pressing in both signals. And then we'd use simple camera resectioning techniques to solve for a relative pose between the touch sensor and the visual signal. And we'd have to do this in each scene because the calibration between them would change over time. And so I like that you can kind of take advantage of the fact that these are, at the end of the day, just ordinary cameras that are being reused for other purposes and use all the tools we've seen in computer vision. And after creating this capturing procedure, we went out and captured a large, or many of these different scenes with something like 19,000 different touches total. But there's one limitation here, which is that these touch signals are still very sparse. We only have the touch signals for a subset of the scene. And so we wanted to see if we could fill in the touch signals in other parts of the scene that we didn't directly touch. And so here's how we'll do this. We'll reuse this idea of using a diffusion model to estimate touch from images. We'll take the NERF that we captured. We'll take a given pose RT of where we want to estimate the touch for. And then we'll just train a latent diffusion model to estimate the corresponding touch from an image and depth map that were extracted from the NERF at that location. And so this will be a way to kind of take the touch signals that we do have and try to use them to fill in the touch signals that we don't have in the rest of the scene. It's a little bit like in-context learning. And I should mention there's a really interesting related work in robotics that has a similar idea. They Coral this year, they have smaller objects they use robotic proprioception for, and they use a GAN to like us, to impute touch. So it's a very nice work that I recommend checking out. And okay, so then this is the result of this procedure. We have a bunch of training probes, and you can see in this overhead view, different locations that we probed. And then on the right, we're going to show generated touch for a selection of different locations in the scene, each of which is close to the places we touch, but not that close. So it's about at least 10 centimeters away in each one. And you can see what this is, we can estimate here what this would feel like. You can see that it estimates that it's an edge. You can tell this is kind of a softer surface. This is a flat surface. And we've seen enough carpet that we know that just like the texture of the surface should look like that. And even though we've never directly touched this table, we can infer something from other tables or from other flat surfaces. And here's some other examples of this. We also have outdoor scenes. We even have some scenes that were collected in snow, which are more challenging. And you can see the model is learned to propagate this touch in kind of this quasi-dense way. And one of the things you can do with this model is you can learn joint embeddings between vision and touch and use them to localize tactile signals in a scene. So you give me a touch signal, I'll tell you where it's located in the scene. And just to visualize this, we can just take a bunch of crops from this image. The true tactile signal is located at the center, and I'm highlighting all of the different locations that it's attending to. And you can see the model, it knows that this is an edge. It doesn't know which one, though. It's one of these different edges, and it's unsure which. Here's another example where we press this fabric, and the model lights up the whole area that has fabric. And one thing that I thought was interesting about this approach was that the imputed touch is good enough that you can use it for training data. So if we train our embedding with the densified, estimated touch versus just using the raw samples we collected, then we get a slight boost in performance on the tactile localization task, which suggests that at least the touch signal we're generating is useful enough that the simulated data may be useful for other kind of downstream tasks. And likewise, in representation learning, you can take the features you learn, apply them to a material recognition task that we developed in our previous work. And you can see you again get a boost from using our data sets and maybe like a small boost from including both the real and estimated data. Okay, so just to summarize this as part of the work, these tactile augmented radiance fields, I think are exciting for the sort of open world setting because you can use these 3D constraints to collect multimodal data in a shared 3D space. You get paired vision and touch for free. There's no occlusion, and it lets you kind of impute touch in other locations. And you can, in principle, collect this autonomously either with a robot, but in our case, we used a human to do it. And I think what makes it exciting is that you could potentially eventually have these sort of models that use 3D to learn about the world in an autonomous way. Okay, so just for the rest of it, I want to talk about some of our other work on learning from audio-visual signals. And we're going to have a different way of learning about the world that doesn't exploit geometry. Instead, it's going to use this idea of an audio-visual analogy. So one of the assumptions behind a lot of audio-visual models and a lot of multimodal learning in general is that you have some paired data. Somebody gives you an image in audio or image in text, and there's a known correspondence between them. Your task is to predict one from the other. This audio goes with this image, this text goes with this image, so on. But in a lot of applications, actually isn't quite what you want to do. For example, in the task of visual to audio generation, merely predicting the corresponding soundtrack for a video isn't always what you want. Sometimes the actual sound in a video is actually not what a user would want to hear. And just as an example of this, the names for the artists that create these sound effects are named Foley artists, and this is how they work. So if you hear a sound in a video, it's made on a sound stage, and the way that the Foley artist produces the sound can be quite different from what's actually happening in the scene. So here's an example.
Walking on leaves or in a forest.
That's what you're hearing when somebody's walking through leaves.
For snow, what we normally use is regular play sand. And then to add to that, sometimes you hear that familiar crunch, which we use cornstarch. Your ear hears snow, but in actuality, it's sand.
So what you're hearing in movies and TV is really this very artificial sound. And so actually, if you were to actually correctly produce the sound that you want in the video, it might not actually be what you need for this downstream application. And so we took inspiration from this work, the classic work from Aaron Hertzman on image analogies. For those who haven't seen it, the idea is given some input image B and a pair A prime, we want to create a new image B prime that relates in the same way that to B as A prime relates to A. Like take the change from A to A prime and apply it from B to B prime. And we can try to do something similar here. We can take a silent input video, and our goal would be to take some conditional audio-visual example and use it to create a corresponding soundtrack with that input sound video. So we're going to make this silent video sound like this other video that does have sound. So this is an appealing idea, but how do we actually get the supervision for this? So this is some work that was a collaboration with some folks at Adobe, led by a former undergrad, Yushi Du, and Xiang Chen, as well as Justin Solomon and Brian Russell. We found that we could sort of automatically create these analogies by taking audio-visual data and creating analogies from it as follows. We will take one subsequence of the clip. We'll call that a conditional example. And then we'll take another sequence in the clip taken from a few seconds before or after. And our goal will be to estimate the audio from that second clip using the conditional clip as a kind of a hint. And this takes advantage of the fact that audio tends to be repetitive. A lot of times if you hear an action, you probably hear a similar action some other time during the scene. And so the model can exploit this conditional audio-visual example as a hint to allow it to fill in audio that it hasn't been provided with. And again, you can think of it again as another kind of in-context learning, but it's one where we have the special time-locked multimodal signal. We have vision and sound that correspond in time. Every frame has a corresponding sound. It's like a very particular type of in-context learning that we're training our model to solve. And so the actual model itself looks like a very standard vision to audio model. We adapted from this very nice work from Yeshin and Ratu on basically applying VQ GANs to sound generation. We'll just tokenize the input video, we'll tokenize the conditional video and audio, and then we'll generate from all three signals together the code of a corresponding audio signal. And then we can convert that then into a waveform. And one thing we found that was interesting here was we could also improve the synchronization of the audio with the video. by using what are called synchronization models. These are models that take a given visual signal, take a given audio signal, and they tell you whether they're in sync or not. And we can use re-ranking, just like flip re-ranking, but with a synchronization signal to rank the audio generations that have the highest degree of synchronization with the input video. So we'll just generate like 100 different audio tracks, pick the one that's most synchronized, and just produce that. And so this lets us do things like take this input silent video of somebody hitting things with a drumstick, and we can take a conditional example of somebody hitting a phone or like a plastic surface and transfer that sound to the silent video. And we can even swap out the conditional signal. Like, what if we make it sound like this instead? Slightly different surface, get this result. And we can take also more kind of real world videos. We can take a silent video of somebody juggling this soccer ball, condition it on this video of dropping ping pong ball, and generate this sound a little bit. Another example, sound video of this ball bouncing, condition it on this drum, and generate this corresponding sound. One more, chopping a vegetable. Again, make the sound like the drum. Okay, so and then finally, one other project that kind of puts both of these threads together, uses 3D constraints and uses analogies together, involves sound localization. So one thing that we noticed that, or that I guess is well known, is that sound conveys changes in camera pose. Like as you move your head around, the direction of this sound source will change in both the visual and audio signal. Louder in your left or right ear, depending on where you're looking, and the visual signal will change in a corresponding way. And so we wanted to see if we could use this idea to self-supervise visual camera rotation estimation systems and audio localization systems. And again, this worked for my PhD students, Young Chen, in collaboration with Xingyi Qian, part of David Foey's group. And we wanted to, again, use this idea, like if you're staring at straight ahead at a sound source, like a ringing phone, and you rotate your head to the right, it's going to get louder in your left ear. So this binaural sound in your head that you're perceiving will get louder in the left ear and softer in the right ear. And then simultaneously, there will be this motion. The sound will move to the left. And so if we can try to use these simultaneous changes in vision and sound to train models that can solve sound localization and camera pose estimation. And one way we can kind of learn, one way to do this is just to learn features using these signals. We can train a model to take all of these inputs, A prime, and B, and try to estimate the corresponding binaural sound B prime. And again, it's like a little analogy. A is to A prime, as B is to B prime. Can you figure out what the corresponding sound in B prime is, given these other inputs? It's a self-supervised learning test that kind of forces you to understand the relative pose and from visual data and the change in the sound direction from audio. And likewise, you can also kind of just fill in one of the two channels. And we found that you could learn features this way. You can train the kind of a cross-view binauralization model that's conditioned on video and learn features that were helpful for camera pose estimation and sound localization. But we also wanted to see if we could use these features for slightly crazier downstream tasks. So what if we just use these two signals to just jointly train a model that can estimate sound directions and a model that can estimate camera rotation? So can we like do this without having any supervision, no labels on sound directions or camera rotation? We'll just force these two models to agree with one another. We'll train the model in particular such that the estimated visual rotation between a pair of frames S and T corresponds to the change in the estimated change in audio sound direction. The predicted sound direction at time t and time s, when you subtract those, should correspond to the visual change and camera rotation. And you can then try to jointly train both these models, the sound direction estimation method and the camera rotation estimation method. There's some subtlety here. There's like ambiguities. You can't tell if the sound is in front of you or behind you. You have to add some constraints to avoid degenerate solutions. But you can actually train these models, and we train them in a simulated environment from Chong and Chen called sound spaces. And what's cool is even though it's trained in simulation, you can apply it to off-the-shelf real data sets. For example, you can take just the camera rotation estimation model and plug it into this Stanford 2D, 3D benchmark. And you can see that the model can estimate camera rotation pretty well, not as well as like SIFT plus Ransack, but actually pretty well. You get like something like a mean error of 1 degree of rotation error on our benchmark. And we can also use the sound localization model to solve sound localization benchmarks, where again, it's not the state-of-the-art method, but it's surprisingly good on a lot of tasks. And we can even apply them both to real video. We recorded this video where we rotated the camera while the sound was playing, and you can see the sound direction corresponds to the change in the camera rotates, sound direction, camera rotation. All right, so just to summarize, I think these sensory modalities like touch and sound are going to be increasingly useful for learning about the physical world and giving you information that'd be hard to learn from vision alone or vision and language, which I think makes it really exciting for open world settings. And in particular, there's 2 ways that we can learn from these signals: 3D constraints that allow us to impute missing observations and sparse signals like touch, and we can use this idea of analogies to do self-supervision and solve a variety of downstream tasks. I want to thank all my collaborators and also thank you. Yeah.
I think the analogy work, what would happen if you gave a condition that was like completely mismatched? Like,
Yeah.
to understand
If it's too far out, it'll probably just ignore it. But it's like really incentivized to use anything it can, because during training it always sees similar data. But yeah, if it's too far out, it just fails. And I should say there's the one limitation there is we can only really deal with these sort of percussive sounds due to the generation method. But I would think it would be interesting to try that with larger scale, training and more diverse data. I suspect that if you add camera cuts, it also might break for the reason you might now have examples where it learns to ignore it. Yeah.
Your touch sensing work. What would happen if you apply this to like truly deformable? Because a lot of the examples you showed were rigid or things which don't really visibly change when you touch them.
That's a great question. Yeah, and I think I think what's interesting about touch isn't so much the geometry part of it; it's the deformation, the material properties. That's something you can't really get from like LiDAR or any depth sensor, and I think that's what makes touch unique. And there's a little bit of that in these data sets, like the grass, for example, and in the touch and go data set where the undergrads capture everything. We do have some of that. But I think that we need to look at it a little bit more carefully, because I think one of the main issues is we're just generating a single touch example here, a single frame, and it doesn't really capture the motion. And so I think we really need to apply like video synthesis to this to really analyze it more carefully. Because I agree, we didn't explore that as much for this work as we should have. Yeah.
For the touch imputation, I guess you're imputing this sort of raw sensor data.
Yes.
But if I build my own gel sensor, presumably its raw sensor data will look much different than what you're doing here. So what's the right way to kind of measure?
I think it's a great question, because the touch signal sensors are really
it's very holistic.
Yeah. I think it's a little bit frustrating that touch is so so diverse. Like it's not like microphones where they're pretty much the same, or other LiDAR where it's like somewhat unified. So I think there's a few different ways to address this. We have a paper on Friday led by Fred Yong, who in collaboration with Alex Wong at Yale, that's about learning embeddings by just taking all of the vision touch data from all the different sensors we could find on the internet and just learning a single embedding for all of those. And I suspect that that sort of approach might be one way to address this. You just collect a lot of touch data, and there's enough similarities in it as a human that you can kind of tell what's going on. Maybe a computer will also eventually learn that even though one sensor is gel site, another is digits, different sensor, it learns what's important there. Another answer that we're exploring is translating between touch sensors, and it looks as though you might be able to just take the touch sensors from two different sensors and predict one from the other. But I do think that it's like an issue that is an open problem in this field. Yeah.
So my question is, what do you think is like the most natural way forward to like scale up this touch and vision data? Let's say to build a multimodal foundation model for touch and vision. Is it like just brute force collection of data, or like something that you can
Yeah, that's a really good question. I think there's a lot of different approaches. One that I didn't talk about is synthetic data. People often generate touch, but I think it's really hard to model like the microgeometry and for the deformation. I don't think there's actually very good physical models there. It's actually a very difficult thing to simulate. But I think that is like a possible source of getting at least some data that you could like pre-train a model with. The other source, I do think that just like the hiring a bunch of people to go out and collect touch sensors is actually a pretty good way to acquire a data set that you might be able to then adapt to other things. But later, I think the ultimate approach would be like to actually have a robot collecting the data. But so I kind of view this work as a way to just kind of get started with pre-training, the same way you might have a foundation model with vision and language. This would be the equivalent with vision and touch, albeit with much less data than the entire internet. But it's just a way to kind of get started ultimately for robotics. Thank you.
Yeah, I'm mute. Make sure your volume is. Do I have my video turned up? Oh, it says no, start your video. Oh, there we go. That's good. Thanks, Shu. Then you can take this and maybe minimize it or put it somewhere in the corner. The videos. Oh, yeah. There we go. Okay. Oh no, how do I make it full screen then? Here. I like that. But do I have it my presenter screen here? No, no, you don't. Wait, then how do I show my presenter screen? Do you know how to do that? Huh? That's a bit rough though. Probably this is the way to go. This is probably easiest. This is okay. 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 All right. Our last session before we break for lunch is a session by Yun Han, who is going to be talking about a challenge, the inaugural challenge on instance detection, which we'll hear more about. So please take it away. All right. Thank you. Hi, everyone. My name is Yun Han, and it's my great pleasure to present our challenge, INSTAT, Object Instant Detection Challenge, on behalf of the organizing committee, including Qian Qian, Yanan, and also Shu. And all right, without further ado, let's get started. So first, what's INSTAT and why we care about this problem? So INSTAT is basically try to detecting a very specific instance from a 2D image in the format of a bounding box. And instant detection is actually one of the fundamental capability of humans. For example, in the airport, like when the passenger is trying to find their luggage
from 100 similar like instance, and they'll be able to quickly and accurately identify which one is their luggages, even though they probably under heavy occlusions, or maybe under different lighting conditions, or maybe have slightly different pose from what they see at their homes. And people mostly able to quickly identify them. And that's one of the fundamental capabilities. And in this case, we try to study instead and to bring this like capability into machines, and also foster like the research into other directions. So in a one-line summary, basically instead we'll be trying to locating the wanted object at distance. And instant detection is also being significantly important in the field of robotics. For example, in a elderly assist robot, if they want to fetch some like object from the kitchens, and they need to first be able to locate the object instance at distance before they make any following operations. For example, the pathfinding, or when they get close enough, they do the grasping. So instead is actually one of the very first steps before the robot takes any moves. So that's why we believe instead is a very important problem. So here we present the protocols for the instant detections. So instant detections, normally they take the two type of input. One will be the testing image, commonly known as like the scene image, or some people also call them query images. And they also take a bunch of like profile image, or so-called reference, basically specify the visual appearance of the object instance of interest. So, for example, here the object instance is provided as object-centric multi-view images with a QR code placed on the tabletop. And by feeding both of these two parts into the instant detection models, and we can see the model outputs the three bounding boxes, which is represent like where's the location of these instances in the 2D images, basically the chip, the mouse, and also the dinosaur. So that's the general protocol for the instant detection problem. So comparing to the well-studied object detection in the literature, so it's very close. Instant detection is very closely related to the object detection, but it comes in with fundamental differences. So object detection aims to detect all objects that belong to some predefined classes. So I think like in the very well-studied, or like very like popular in the previous years, autonomous driving like applications, some of the most common classes will be some like vehicles or pedestrians, or maybe cyclists, while instant detections actually try to detect a very specific object instance, and they define by some visual examples. In this case, each of the instance will be treated as a separate class. For example, taking the coffee beans as one of the example, if we want to detect the coffee beans in the object detection, then all the three coffee beans showing on the top should be detected. While if we try to detect the coffee bean in the instant detection, then we first want to specify which instance, or which like a coffee bean bag we want to detect. Obviously, there's three, right? And only one of them we want to detect. And that's the fundamental difference between the object detection and the instant detection. So in the past, instant detection problem mostly developed in the closed world. By saying that, basically, we feeding the profile image of the instance, and also some like background image randomly sampled and majorly follow the cut-paste-learn method. Basically, what cut-paste-learn do is that they cut the foreground of the object instance and then try to paste them onto the random backgrounds. And then, because since the code actually controls where's cutted like the foreground pasting onto the background, so this actually produced the free annotations. And then by doing this, this strategy is able to produce or synthesize a large amount of training data. And then following this, the pipeline will train a detector by treating each of the instances as a different class, and then with the free annotations. That's the so-called the closed world setup. Basically, after the train, the detectors they will try to detect these like predefined object instance, and then try to detect it with the incoming query image during the testing time.
However, we want to point out by sampling this random background, it is already an open world strategy in terms of since this randomly sampled background is coming from the internet, and so it could be any images like during the data synthesis process. Therefore, we believe we want to just point out developing. So the previous copy-paste learn strategy is one of the insufficiently way to use the background image in the open world. So right now we want to advocate developing incident detection problem in the open world. So basically, not only we want to utilize the open world sampled background images, we want to also leverage the open world trained foundation models. So as we can see, both of the background image and also the models are learned onto the open world data, which is like at the internet scale. And these foundation models are generally trained for the general purposes, and we adapt these foundation models as a specific like model for the incident detection task. And so these adaptive foundation models will be used for the testing, and we still follow the same protocols. At the testing time, we'll be feeding these profile images to specify the object instance for interest. And of course, we're feeding the scene images, and together, these adaptive foundation model will output the bounding box of the object instance of interest. So by the way, this is also the general pipeline for the challenge winner this year. So then let's dive deep into the challenge. So beginning with the challenge data set. So our challenge data set comes with 100 object instances, and each of them come with 24 profile images, and they capture with object-centric manner. Basically, we capture at every 15 degrees in azimuth and around 45 degrees in the elevation view. And we also place the QR code on the tabletop. This is for the potentially falling like to compute the camera pose with the COMAP. So for example, with COMAP. And these profile images come with a high resolution, basically around 3,000 by 3,000 pixel resolution. And for our testing scenes, we come with a diverse different indoor scenarios. And we have 160 validation images and 320 testing images. And all these testing images are extremely high resolution, basically around 6K by 8K in pixel resolution, and they cover diverse scenarios. And also they come with very challenging cases. For example, many of the instances may be heavily occluded, or maybe they are extremely cluttered. For example, in the kitchen scenario on the bottom right, you can see many of the instances are cluttered together, and the model need to be able to detect each one of them in this very cluttered scene. And also in the maybe the top left one, as we can see, for many of the instances, they are extremely small and also far, and they are partially occluded by the shelf. And these are all the challenging cases that the previous data set doesn't come with. And some do's and don'ts for our challenge. Basically, we try to advocate doing the challenge in the open world. So we basically allow the challenge participant to pre-train on anything. Basically, we encourage them to pre-train on the open world data or curate any of their own training data set, and basically leveraging any powerful foundation models for the purpose of the incident detections, except they are not allowed to train on our provided validation and testing images. And other than this, they are allowed to do anything to basically detect all these instances. We also provide 200 indoor background images, which we randomly sample from the background. That shares a little bit similar layout or office lookings to these validation and testing images. A little bit comparison against the existing data set. So in the past, most of the incident detection models are mainly developed on the GMU dataset or AVD dataset. As we can see, they only come with 23 or 33 instances, which is not that many in terms of the modern scales, and their resolution also a little bit lower. In comparison, our dataset comes with 100 instances, which all features these multi-view object-centric views, and it covers 14 or more diverse indoor scenes, covering, for example, office, like kitchens, and different diverse indoor scenes. and it's also publicly available. And we believe this is a better data set right now to foster the problem, to develop the problem of the instant detection in the open world. In terms of the challenge evaluation metrics, we're following the spirit of the COCO data set, adopting the average precisions, aka AP, and they are over different IOU threshold with 0.5 to 0.95 with a step size of like 0.05, and similar for the average recall, aka AR. We also tag the scenes with easy and hard, depends on their clutteredness level and also the occlusion levels. This is kind of like a based on the human judgment. For example, if we see the object instance in the scenes are mostly very small and they may be mostly heavily occluded, then we just manually tag them as the hard scenes. And if the objects are sparse and they are fully visible and also big enough, then we just tag them as an easy scene. Of course, we also evaluate them across different scales. This is determined by the size of the object instance shown in the testing images. By plotting the statistics of the data set, we determine the areas which is less than 200 pixel squares will be determined as small, and between 200 to 400 will be medium, and over 400 will be determined as the large. And so this is, we follow the same labels for the AR. And okay, now it's time for the exciting leaderboards. So this year we have 13 teams and 30 submissions, and many of them are being very competitive. So we talked we have just basically in-depth conversations with all these teams and try to summarize their methods and also collecting what type of data they are using. And we summarize these methods and also results and presented in the following slides. So before we goes into the sophisticated approach developed by the challenge participant, we want to begin the method review from the old days, which is the very beginning of how people do the instant detection before this deep learning era. So in the past, most of people do this instant detection problem for by using this key point matching based approach. As you can see, given some profile image, and they compute these descriptors, for example, like SIF, and then they try to match these key points or doing some template matchings to detect the object instance in the images. And of course, we also want to mention the strong baseline, which is the copy-paste learn, which we have already mentioned before. And here is a general pipeline for how copy-paste learn works. Given a bunch of visual descriptions or profile image of each of the object instance, of course, I cut it already cut it with a foreground, and by randomly sample some background images, for example, this case will be an indoor scene, and the copy-paste learn strategy just to try to randomly paste these object instance onto the background image without quite following any physical surfaces. But you actually try to synthesize very many diverse appearances, try to simulate the potential diverse changes in the testing cases. Even though this approach looks a little bit naive, but this has been proven to be very effective, and this is a very strong baseline and has been dominant for years until the very recent, before the emerging foundation models shows up. So some remarks in terms of the copy-paste learn strategy. First, it generates these free bounding boxes. So one of the major challenge of adapting the major object detection models for the instant detection will be a lack of large-scale annotated data set, while copy-paste learn enable us to synthesize almost an infinite amount of numbers training data to train the detector side by treating each of the instances as a separate class. And yeah, as we said before, you can generate almost infinite numbers and synthesize any appearance with these like from these profile image, maybe we can just by rotate or like by 2D rotation to synthesize a little bit different appearances. As we pointed before, it's insufficiently use of the open world background images. Since you only randomly sample some background image, open world background image, but without leveraging the other open world models and open world data. So nowadays we leverage the open world foundation models to approach the instant detection in the, of course, open world. And so let me walk through the pipeline here. The very first step will be the proposal generation. This step we leverage the SAM, which is one of the foundation model. It can basically detect, exhaustively detect all the object instance in the scene. As you can show, that's one of the illustrated figures like showing on the bottom left. So SAM here basically serve as a purpose of the just the foreground instant detection. And they just need to exhaustively generate all the instant they see in the images. And in the second step, all the generated proposals from SAM will be feeding into another foundation model, which is DynaV2. This is a self-supervised internet scale model, which will be extracted very meaningful features for all the proposals. As you can see, that's like all the proposals from this like testing image. And by extracting the features of the profile images and also the proposals, we have a collection of the instant features and also the proposal features. Next, we try to do a cosine similarity matching between the proposal features and also the profile features. And for each of the proposal, we'll try to rank and select the most similar looking instance, and then basically assign that as the final prediction of that instance. So as you can see, eventually we use the stable matching, and so that's a small dot, a yellow dot, or like that yellow object in the middle will be in this case will be matched to the green object showing on the right. Even though it's wrong, but it demonstrates how this like matching step here is done. Some remarks in terms of this like SAM plus DynaV2 features. You first explore the open world models, the SAM and DynaV2. These two models are both trained with open world data, and it's on the internet scales. But it's one thing to notice that this is a non-learned method. So both SAM and DynaV2, we can see the snowflake signal over there. It seems that these models are frozen, and none of them, the weights is not being tweaked. So this non-learned method actually achieved the new state-of-the-art approach. And SAM actually achieved a very high recalls. Basically, it just means that you can detect almost all the object instance, but we just might not be able to match it correctly. And DynaV2 is also a powerful representation. Motivated from this, like many of the challenge participants see the high recall from SAM. So they are thinking about fine-tuning the DynaV2 to achieve like more accurate feature matching step. And that's actually one of the leading participant do in the leaderboard. So basically they try to learn some like feature representations, and from the experimental results, it shows like a little bit of learning to adapt these foundation models for the specific task of the instant detection, actually make it actually improve the performance. And we have seen submissions that try to fine-tuning the DynaV2s with cross entropies. Basically, for each of these instances, they try to treat it as a separate class, and they do the cross entropy for the classification. And we also see some teams using metric learning. The intuition behind this will be they just try to naturally grouping the profile image belong to same instance closer in the feature space. And we've seen like many teams that try to fine-tune different top layers of the DynaV2. And in the just like the key takeaway in this slide is a little bit of learning for the foundation models or like foundation model adaptation is actually very helpful in terms of approaching the instant detection in the open world. Next line of strategy is try to augment the profile images in both the training and the testing. So in terms of the training will be just as the previous slide shows, by augmenting a little bit more profile images, and they could still following the cross entropy or metric learning to fine tune the weight of the Dino V2. And in terms of adopting these strategies during the testing, then most of the team try to adopt this still following the previous state of the art, which is SAM plus Dino V2, basically using these additional profile images for the matching. So these like additional profile images provide more diverse. So they expect to getting from these additional profile images, they try to capture more diverse features and to achieve like more accurate matching results. So of course, the first line of thought we see will be using standard data augmentation. Here we see mostly will be some like affine transformation, something like skew rotations, and or like even some standard crop. And so another line of thought we have seen will be using commix. So the idea behind the commix will be try to blending the patches from two objects and merging them into a new object. And this is try to hallucinate some different visual appearances and try to augment the profile images. We have also seen people using NERF to render novel views to augment the profile images. This is pretty natural considering we already placed the QR code and the people estimating the code map. And by perturbing the camera pose, they're able to render some novel views. Some qualitative results, like by using learnable features, we have seen right now, most of the teams still developing these in the closed world, performing the best. And by using some like open world approaches that is performing the second, and then with the baseline here will be the non-learned method, which are using SAM plus Dino V2. But we have seen some like more robustness coming from by using the open world models, which we will be showing in the visualization later. This results actually highlights the potential of like developing the models in the open world, and we're expecting to see more sophisticated methods coming in, and eventually we expect that the open world will be outperforming or performing the best. A little bit of quantitative results on the augmented line of approaches. We have seen right now the standard transformation performing the best. So we believe the standard transformation actually is done on the fly, and they're able to synthesize very diverse views in both training and testing. So that's why they're performing the best. Of course, NERF render novel views, they actually being very high quality and also very realistic looking, but they are kind of like come with a fixed views. So basically, we've seen submissions that they generate a fixed number of views, and these views will be fixed in the training and the testing. So the model might be overfitted to these views. So that's why they perform the second. And among all these approaches, commix performed the worst. And this is probably not very surprising considering the quality of the generated images. So it might be too trivial to fine-tune a better model with a commix. But it is maybe worth to investigate using commix in the feature space. So right now we have seen most of these are done in the RGB levels, which is a little bit trivial. Maybe by bringing this strategy into the feature space, we might see some more like performance improvement. And here's some visualizations, and the yellow box showing on the left will be the ground truth, and of course the number there will be show the instant detect, the instance index, and the blue shade is just representing the predictions. And now we have seen like the closer world model performed the best. In this case, like the SAM plus Dino V2 and the open world model both making some predictions, while the closer world models actually accurately detect all the instances in this images. In this like visualization, we have seen On the rightmost bottom, we can see open world model actually find this object that is that has been making mistakes on some closed world models, which is like this. Of course, on the average, the closed world model performed the best, but in many cases, we have seen these challenging instances are being detected robustly by the open world model, which is still highlighting the potential of like modeling the problem in the open world. Of course, the non-learned approach, they just are using the fixed weights. So in comparing to these like fine tuning or using additional like profile images, they perform the worst. But still, like these like are already way better than the previous methods using the copy learn, which is developing the models in the closed world. So from this perspective, we still encourage like or we expect to see more methods trying to develop the trying to approach the instant detection in the open world. So looking to the futures, we have a few like suggested like future directions. First, we'll be try to better exploiting the open world data. So right now we don't see many of the challenge participants trying to collect a large scale of the open world data, and none of them actually try to use like synthetic data in the open world in the large amount of scales. And so we feel this could be one of the very promising directions if we could carefully curate a data set. So that's one promising direction we think about. And the second interesting thing to discuss will be the novel instant detection. This is one of the future focus as well. So right now, for the instant detection, all the object instance we try to detect at testing time are all available for the model to train during the training time. So basically, the collection of the instance during training and testing are all the same. While we have seen some related work focused on the novel instance detection, and in that case, the object instance trying to detect at testing time are not available at training. So basically, we train a model, and at testing time, we provide some profile images and some testing images. The model should be able to handle these unseen object instance and still be able to detect these object instance at testing time. So that's still one of the interesting problems, and it could be go parallel with our instant detection problem. And lastly, it will be interesting to explore some efficiency in computing. So right now, one of the problem with these foundation models is that they could run very slow, while most of the instant detection application could be on robotics, which they are actually require some real-time processing time. It might be interesting to try to explore some knowledge distillation or trying to explore some lightweight foundation models to make the model run faster. And it will be also interesting to explore some like adapters between the foundation models and also their output to make the model runs more efficiently. So these are all the three suggested directions we summarize for the future research. And that'll be all. Thank you so much for listening. So yeah, feel free to ask any questions like if you guys have. All right, cool.
Okay, thank you so much.
Thank you.
Yes. So what is it so?
It's on the calendar link that you have.
Because this is
recording in progress.
So you, then in that case, you can turn this off.
Okay. Do I have to stay connected through audio?
No,
Okay.
otherwise there'll be an echo. We need to sync to your computer,
Right,
just so we can check the projector.
sure.
Hopefully this works. Beautiful. Okay. Okay, I think we're good to go. We will get started in 5 minutes. Yeah. So, Yunhan here will introduce you. And then we
Okay.
can get started.
Okay,
Sounds good.
thanks, good. Do you mind not recording?
Yeah.
Yes. Yes. So the meeting is being recorded.
Maybe we can just try to turn off the recording option.
Is it possible for me to turn on, stop recording?